Learn how to train a language model from scratch that can mimic anyone's unique communication style using your own WhatsApp or Telegram chat data. This course walks you through the complete process, from data extraction and cleaning to tokenization and transformer architecture implementation, giving you the skills to preserve someone's voice or create models for underrepresented languages. Imad Saddik developed this course.
Hi everyone, and welcome to this new course on freeCodeCamp. My name is Imad, and I am here to guide you step by step on how to pre-train and fine-tune a language model in your language. This course covers many topics, so I have decided to divide it into two parts. In the first part, I'm going to start small. I'll show you how to load a small dataset and later train a small language model. This part will allow us to understand the individual concepts clearly. In the second part, which I called Less Scale, is made to show you how to use large datasets and how to train models with large parameter sizes. In this course, you will learn the full pipeline. The first step consists of taking the dataset. We are going to work with textual data. Later, we are going to train a tokenizer with the Byte Pair Encoding algorithm. A tokenizer is used to convert the text into a sequence of numbers. These are the individual tokens that the model will train on. Later, I will show you the transformer architecture, which is used to create the language model. And then, after creating the model, after encoding the data, we are going to start the pre-training phase. At the end of this phase, we are going to get a base model. Later, in order to create a conversational assistant, we are going to create a supervised fine-tuning dataset that we will use in the fine-tuning step. And at the end of the pipeline, we are going to get an assistant that we can chat with. Since we have a lot to cover, I recommend taking your time. Learn each part slowly because this course is made for beginners, so don't worry about any concepts. You can find all slides, notebooks, scripts, everything I have used in this course in the link that I will make sure to put in the video description. Also, if you want to connect with me, I will make sure to link my LinkedIn profile, or if you want, come to my YouTube channel or connect with me on Discord. I'll be happy to chat with you. Now let's get started. Hello, welcome to this course. Here you will learn how to train a language model from scratch. The model that you will train will be able to chat like you or anyone else you want. You will learn how to use chat messages from apps like WhatsApp and Telegram to train your own model. I made this course because I was curious and wanted to understand the full process of training a language model. In this introductory video, I will explain what you will learn in this course. Why take this course? One reason is that it is amazing to use math to copy the way someone talks. This could even bring back the way a person spoke, even if they are no longer alive. Another reason is to learn how to train a language model step by step. We will look at data extraction, data cleaning, tokenization, and more. Also, I am from Morocco and we speak Darija. But when we type, we mix French and Arabic letters and sometimes we use numbers too. This makes it hard for a language model to understand. If you look at the image, and if you are a Moroccan person or someone from Algeria, you will understand what I said here. And you will see that the model is not that great because, training a very big model to learn everything is not going to work, especially for our own language. So this is why I wanted to train a model specifically trained only on Darija. And let's see if it can learn this language well. How do we do this? The first step in the pipeline is data extraction. You need to get your chat messages. You can extract them from WhatsApp, Signal, or Telegram. You can use group chats or private conversations. This is useful if you want to train a model on a rare language. Next, we combine the text. The raw chat data is in a back and forth format, but what we need at the end is to concatenate the text in order to have a sequence of text. The third step is text encoding. We will use BPE, which stands for Byte Pair Encoding, to create our vocabulary and encode the text. You can learn about BPE and tokenization from these three sources. You have this Wikipedia article, this HuggingFace course, and Karpati's YouTube video. After running the BPE algorithm, we will have a vocabulary. Each word or part of a word will have a unique ID. Then we will encode the text using these IDs. Next, we will build the transformer model from scratch. I will do my best to explain it, but I also recommend watching the StatQuest video. It explains transformers very well. Now we will train the model. We will split the data into two parts. Training data, this is going to be used for learning, and validation data. This one is going to be used to check how well the model is learning. After training, we will have a base model. This model can predict the next word based on the training data, but it is not very useful yet. To make it useful, we need to fine-tune it. We will create a fine-tuning dataset. The orange section is where you put the messages of the person you want to imitate. If you want the model to chat like you, then put your messages there. In the last step, we fine-tune the model using this special dataset. After this, the model will be able to mimic the way that person talks, but the hardest part is choosing the good fine-tuning dataset because it affects how the model behaves. Are you ready? Let's begin. Hi, in this video, we will talk about data extraction and data processing. I will focus on exporting your conversations from WhatsApp because this is the main application that I use, but for other applications like Telegram or Signal, I will make sure to put links in the video description to help you extract the data from them. Extracting all conversations from WhatsApp can't be done by just one click. You have to export your conversations one by one. This is tedious and makes the process manual. Here are the steps that you should follow to extract the conversations in a TXT file. First, click on the three dots on the top right corner, then click on the More button. After that, click on Export Chat and choose Without Media. If you want to include media, then you should add more processing steps. For people who speak well-known languages, it will be easier for you to extract the text from audio files. For images, you can use vision models to give you a description of the image. In my case, I skipped this because there are no good models that can do speech to text in Darija. Here is the pipeline that we will follow. The first step is exporting the data. In the case of WhatsApp, the format will be like this. You have the date in this format, then you have the name of the person who is talking, and finally the message. The second step in the pipeline is applying filters to the exported data. We need to do this because the data should be cleaned. We need to remove links, special tags like media omitted because we skipped exporting media, so WhatsApp will replace them with this tag. If you deleted the message, you will have this tag, so we need to remove these. We need to remove email addresses. I mean, here, if you are using the model for you, you don't need to do this, but if you are planning to share this with people, then please make sure to remove confidential data. We will remove tagging and we will apply other filters. We will see this in the notebook section. And finally, we will concatenate the cleaned data into one giant sequence of text. This output will be used in the next video, where we are going to talk about byte pair encoding and tokenization. Now let's code. Go to the video description because you will find the link that will take you to my GitHub repository. Clone the repo. It contains the slides and notebooks. Open the project in your preferred IDE and follow me. Open the left panel, open the data folder, and put every TXT file that you exported from WhatsApp inside the private folder. Then open the notebooks folder. Currently we have just one notebook. This is the one that you need to open. And let's start. In the first cell in this notebook, we have the read WhatsApp chat method. This one will take a file path to read the file and then apply the filters. We define them here to remove unwanted messages. As I said, inside the read WhatsApp chat method, we are defining our filters. Some of them are easy, while others are a bit confusing because we are using regular expressions. But I will make sure to explain this in simple terms. The encryption message filter will discard any line where this text appears. If you are using another language, please modify this accordingly. I was using English, so this is why it appeared in English. But if you are using French or Arabic, then this string should be modified. The media pattern filter will do the same. It will remove any lines with this tag. As I said in the first section, this tag is added when you decide to export the data without media. Email pattern and URL pattern will filter emails and URLs. And here we are using regular expressions, as I said, to catch those emails and URLs. You don't need to understand this fully, but as I said, these are going to find emails and URLs and remove them. The edited message filter will just replace this tag that you have here with an empty string. The next four filters, deleted message, null message, created group message, and added you to group message, are going to discard rows with these terms. If we find rows with these terms, we are going to remove them. Finally, the tagging pattern will replace any tagging with an empty string. I hope that you understood those filters. After that, we are going to read the file and we are going to read it. We are going to extract the lines from it. After that, we are going to iterate over all lines and apply the filters. If the filters are not met, we will keep the line. But if that is not the case, we will discard it. Inside the if statement, we replace the edited message string and tagging with an empty string and strip the resulting string. After that, we basically add the line to the filtered lines list. The following regular expression is designed to extract the timestamp, sender, and the message to basically create a data frame. I chose to store the data in a data frame because it will make it easier to look at the data. Now, run this cell. You can see that we were able to execute it without any issue. Now, in this cell, we are going to use that function. First, we are going to loop over all the files that exist in the private folder. We will extract the file name by using the stamp property and store the data frame in this all chats dictionary. Let me execute this. Behind the scenes, I have a lot of files, but because that data is confidential, I'll try to basically use a dummy dataset just to show you how the data frame looks like. As I said, this is just a dummy data frame just to show you how it looks like. In the first column, we have the timestamp, we have the sender and the message. As I said, I chose the data frame because it will make it easier for you to look at the data instead of just looking at it in the TXT file. In the next step, we are going to concatenate every message in the message column into one big string. Let me run this. In my case, this string contains 1,430,000 characters. This is a lot, but the more you get, the better the performance will be when we are going to train the model. In the next video, we will take this text sequence and apply the byte pair encoding algorithm on it to create our vocabulary and to encode the text sequence. See you next time. Hello everyone. In this video, we will talk about text encoding. This step in the pipeline is very important because it affects the behavior of the language model. Language models are not trained directly on text. If you take a transformer model, you cannot give it a sentence, for example, how are you, and train it. This is not possible. Instead, transformers work on numbers. If this time I feed this list of numbers to the model, it will understand it better. Converting text to numbers is what we call encoding, and it can be achieved with these methods. We have character level encoding, word level encoding, and byte pair encoding. Let's compare these methods. I will use this sentence as an example. Here is a table that summarizes the comparison between the three methods. Let's start with the sequence length. The character level encoding has the highest length, while the word level encoder has the lowest. The sentence is split into characters in the case of the character level encoding, and in the case of the word level encoding, it was split by word, while the BPE algorithm divides the sentence in between. So here sometimes you will get words, sometimes you get subwords, etc. The vocabulary size is the number of tokens that you will extract from your dataset. These numbers will vary depending on your use case. Generally, character level encoders have very small vocabularies, while word level encoders, especially if you use multiple languages, will have the biggest vocabulary. You should always aim to find a compromise between the vocabulary size and the sequence length. Generally, if the vocabulary size increases, then the sequence length will decrease, and vice versa. We can see this behavior in the table. For the character level encoder, we have a small vocabulary, and as a result, the sequence length is big. We don't want this because working with very large sequences will fill the context window of the model very quickly. On the other hand, the word level encoder uses a very big vocabulary. This is good because the sequence length now is small, but the problem is that this is computationally expensive to run because you will have very big matrices. It will slow down the training significantly. This leaves us with the BPE algorithm. The great thing about it is that we can control the size of the vocabulary based on our hardware and the data we work with. Now let's try to understand this algorithm. BPE stands for byte pair encoding, and this is an algorithm designed to compress text into a small sequence. Let's see how it works through this example. Let's start with this sequence of text. The first step is to convert it to a list of bytes. After that, we compute the number of times each pair appears in the sequence. For example, 97,97, this pair occurs 4 times in this sequence. After computing the number of occurrences, we will try to find the max pair, and we will replace it with a new token. I chose 666 because it doesn't exist in the vocabulary. And then what I will do, I'll just replace 97,97 with this new token. The step that we performed here is called a merge step, and we can continue from there. We will take this list of bytes, we will do the same thing. We will compute the number of occurrences, We will search for the pair that has the maximum number of occurrences, and we will replace it with a new token. And this is the second merge that we performed, and we can perform other merges if we need. As I said before, the byte pair encoding allows you to define how many merges you want to perform so that you can control the size of the vocabulary. So if you want to perform just 10 merges, you can do that. Once you reach that last merge, then the algorithm will stop and you will get your vocabulary. Finally, I want to share with you these links if you want to read more about the BPE algorithm. You have Wikipedia articles, YouTube videos, and this GitHub repository that we will use in the coding section. And this is exactly what we are going to do now. Before showing you the notebook, go to my GitHub repository and pull the latest changes that I pushed. I am changing this repository regularly, so make sure that you have the latest changes. And I mentioned this min-BPE repository. It was created by Andrei Karpathy. It will allow us to use the BPE algorithm efficiently without making it ourselves. But I made sure to link Andrei's video because he explained the BPE algorithm very, very well. So here I opened VS Code, and here you can see that we have two notebooks instead of just one. I want you to open the first notebook because I forgot to do something in the previous video. If you scroll down, here I added a new cell that will store the text sequence in the output folder. Make sure to create this folder if you don't have it because it is ignored. I have already done this, and I have rerun this notebook, and if I open the output folder, you can see that I have the sequence text. So please make sure to rerun the notebook in order to generate this file because we will need it in the second notebook. Now close the first one and open the second notebook. And this is exactly what we are doing. So please load the sequence of text. Here are the number of characters that are in this text sequence with the data that I have. Here, as I said, I am using the min-BPE repository. Sadly, this project, you cannot just use pip install because it wasn't added to the PyPy repository, but I made sure to clone it and I kept just the scripts that we need. So they are already included. So if you pulled the latest changes, you should be able to have access to this repository. Because I need to import the min-BPE to the notebook, I have added this cell. Here I used the sys module to add the parent directory to Python's system path. If you don't do this, then Python will not be able to recognize where does the basic tokenizer exist. So here we are importing the basic tokenizer from min-BPE. There are many more tokenizers that you can use, but for me, the basic tokenizer is enough. So let's just use it. Here you create an instance of the basic tokenizer. You take that object and you call the train method. The train method expects two things. It expects the text sequence. This is the string that we exported from the first notebook, and the vocabulary size. This is what I said in the slides. You can configure the BPE algorithm to give you an exact vocabulary size. It's not like using word or character level encoders. This one, you can customize it however you like. So let's just run this. This will take, I think, 1 to 2 minutes. It depends on the size of your dataset. For me, I have 1,400,000 characters. If you have more, if you have 10 million, 100 million, you will need to wait more. So I will wait for this to finish and I will come back. I am back. And as you can see, training the tokenizer took 1 minute 51 seconds. Now we can inspect the vocabulary. The tokenizer has this vocab field. If I run this, it will give me the content of the vocabulary. These are the tokens that we will use to encode the sequence of text. And here, the great thing about this is that it was able to pick up my name because it was occurring a lot in the data set that I have. So as you can see, this is promising. So make sure to look at the vocabulary just to make sure that there are no problems, and then you can continue. So here we can test the tokenizer. Here I have this simple string. And as I said, here I am using the Darija language, but you can change this to your language if you like. Just make sure that the dataset that you started with contains the same characters. For example, if I speak Chinese and I used a dataset that contains only Chinese characters, then if you use other characters, if you want to use that encoder to encode English text, it will not work because the tokenizer has not seen any English characters. Okay, so make sure that you use the tokenizer for the specific use case that you are trying to solve. So if I take this string and encode it, it will give me this list of tokens. So I can take this is exactly what I did, and I need to make sure that if I decode the same list, I should get the string that I started with. And this is exactly what we got. Now let's continue. Here in this section, I am talking about special tokens. I am going to add them to my vocabulary. Why? Because I will need to use them in the fine-tuning step. I know we did not reach that step yet, but this is very important. We need to have this because the model will use these tokens in the fine-tuning step. You can see that here, for example, we have this token that is called end of text. If the model outputs this token, it will stop generating tokens. Currently, if we train the model, we will get a base model. It will never stop from generating tokens. Why? Because in the dataset, we don't have this token. But in the fine-tuning step, we will create a dataset that will contain these special tokens to train the model to stop, for example, generating the response, or to use the start and end of text. We have this separator. If it encounters characters that it has never seen, we will use the unknown token. So this is why we need to add these special tokens. So let's just do that. You can see that here you have this special tokens field from the tokenizer. We can basically just give it a dictionary, and we will make sure to save the tokenizer. This is the last step, so that we don't repeat these steps every single time. And here, what you can do, so you can take the tokenizer and encode the sequence text. I did that and I got 618,000 tokens. This is it's not that bad, but if we could add more, that will be even better. And this number, we are going to use this in the training and validation steps. If you are familiar with open source large language models, you will see that they were trained on a big chunk of the internet, and the training set contains trillions of tokens. But because this is a small project, I mean, having 618,000 tokens, it's not that bad. So when we start training the model, we will see if this is enough or not. The last step, as I said, is saving the model. Here I have created a new folder inside the output directory, and here we have the tokenizer. And as you can see, MinBPE was able to add these special tokens that we added manually, as well as the other tokens. Okay, so we have everything here, and I will show you when we start training the model how to load this tokenizer. We arrived at the end of this video. In the next one, we will create the transformer model from scratch. See you next time. Hi everyone, I hope you are doing well. In this video, I will talk about the transformer model and how do we use it to train it to learn language from the training dataset. The transformer architecture is used to train language models, and it is divided into two parts. We have the encoder and the decoder. For tasks like machine translation, we use both parts. The encoder is used to encode the sentence in the first language, and the decoder tries to generate the translation of that sentence based on the information given to it by the encoder. But if you want to train an autoregressive model to learn from the data and to generate text that is similar to the data distribution, then use just the decoder. Now let's focus on this part of the transformer. The decoder is composed of these components. First, we have the token embedding layer. This layer turns each token into a vector. In the table, you can see 3 tokens, and each one has its own vector with n values. Using vectors helps store more details about each token, which is much better than using just one number. Next, we use positional encoding to keep track of the order of the tokens. If I take this sentence as an example and break it into tokens, each token gets a value that shows its position. For example, high is the first token, so it gets 0, then 1, etc. But again, instead of using just one number, we use a vector to store more information. We will see this in the coding part. Now we reach the self-attention mechanism. Its main job is to understand the relationship between different tokens in a sentence. This is crucial in language modeling because the meaning of a word often depends on the words around it. Self-attention helps the model focus on the most relevant words, no matter where they appear in the sentence. This allows the model to capture context and meaning more effectively. We also have residual connections. These are important because they help information flow smoothly throughout the network. Without them, the gradients might become too small during training, making it harder for the model to learn. Between layers, we apply layer normalization to keep the model stable and improve learning. It helps by standardizing the inputs to each layer, making sure they have a consistent range of values. Feed-forward or MLP layers are added to increase the model's ability to learn complex patterns. We can combine the self-attention mechanism, MLP layers, and layer normalization into a single unit called a block. This block acts as a built-in unit of the transformer model, and we can duplicate this block multiple times, allowing the model to learn more complex patterns. Finally, we have the final layers, which are the projection and softmax layers. These layers help convert the model's output into a probability distribution. This distribution shows the likelihood of each possible next token. By sampling from this distribution, we can predict the next token in the sequence. Now let's talk about the parameters that we can set. The block size defines the maximum sequence length that the model can handle as input. The embedding size refers to the size of the vector used to represent each token. The number of heads and head size are parameters used by self-attention layer to process different parts of the sequence in parallel. Lastly, the number of blocks determines how many times we duplicate the block. Finally, before going to the coding section, I highly recommend checking out the StatQuest playlist and Andre's video. These resources are invaluable and you will learn a lot from them. I intentionally didn't go into too much detail because they have already done such a great job explaining the concepts. Now let's create our transformer model. Make sure to open the third notebook in this series. Here we will start by loading the tokenizer. Again, we'll use system so that we can access basic tokenizer from the root directory. I already saved the tokenizer in the previous videos, so watch that if you haven't. And here we are going to use the load method in order to load our tokenizer. So let's do that. Now we have this helper function, which is called getVocabSize. It will basically give us the size of the vocabulary. We will take the vocab and special tokens and sum them up to get the vocab size. As I mentioned in the slides, this implementation of the model was inspired by Andre's implementation of the GPT-2 model. If you want to watch that video, then please click on this link. And before showing you the code, I would like to show you this part where I explained visually how the transformer model handles the input. The first step is word and position embedding. In this step, we start with a sentence. We use the tokenizer to split this sequence of text into a sequence of tokens. Each token has an ID in the vocabulary. For example, this one has 32, 59, etc. And the shape of the sequence is 1 by 6. 1 refers to the batch size because we have just one example, and 6 refers to the number of tokens. Next, we use these tokens to find the corresponding embedding vector for each token. Basically, this is a matrix. If let's say that we have a vocab size of 1024 and the embedding size is 768. In this case, we will use, for example, let's take this token as an example. So this means that we will take the 1000 row and take that specific vector. That vector will be learned during the optimization process to encode the doing token. And we will do the same here for position embedding. And here you will notice that we have a difference. Here we have 1024, but here we have 256 because position embedding is tied to the block size. And here, this means that the model can only handle sequences with up to 256 tokens. If you try to feed the model more tokens, that will not fit because the matrix is small. After getting the token and position embeddings, we add them together. This results in a tensor of size 1 by 6 by 768, where 1 is the number of inputs, 6 is the number of tokens, and 768 is the size of the embedding vectors. This output is then sent to the block layer. The second step is the multi-head attention layer. Here we take that tensor that we got from the first step and pass it to the multi-head attention layer. This layer has two settings. We have the head size and number of heads. These settings split the attention block into smaller parts called heads. All heads process the input at the same time. This is why we have so many arrows, because each head will process the input X independently, and this calculation will be done in parallel. The goal of multi-head attention is to have the model focus on different parts of the input at once. Each head can learn to look at different relationships between words or tokens. Since they work in parallel, the model can understand patterns in the data more effectively. Each head produces a tensor of size 1 by 6 by 128, where 6 again refers to the number of heads this time. It's not the number of tokens, and 128 is the size of each head. We then concatenate the vectors to end up with this tensor of size 1 by 6 by 768. And as you can see, I tried to color each row to indicate the different heads that compose this tensor. Finally, this tensor is passed through a feed-forward layer, which adjusts the last dimension to 768, matching the embedding size. In this example, I did the calculation to have 768 here, so there is no need to add the feed-forward layer. But if this value was different, then we have to make sure that this value matches the first tensor, because we are going to use the number of layers to duplicate the blocks. And we want the output of one block to be the same as the input to the other block, so that we can stack them sequentially. Finally, we arrive at the prediction layer. Here I try to condense all the previous steps in these three dots. Here is the input sequence and here is the output. After the final attention block, the output is passed to the prediction layer. This layer contains a dense layer that reshapes the output from 1 by 6 by 768 to 1 by 6 by 1024. And 1024 is the vocabulary size. Why we are doing this? Because in the end, as you can see here, we get a probability distribution. We might get different probability distribution depending on what we give the model as input. So this is what I tried to draw here. And this allows us to sample from the probability distribution to get the next token in the sequence. I hope that you found these visualizations informative. I tried to create them to show you the steps visually because it will help you understand the concept instead of just looking at the code. Because you can find the code online. There is no problem with that. Transformers are now well understood, so I wanted to pay more attention to what goes under the hood. So let's start looking at the code. First, let's define the hyperparameters. We are setting the seed to this value to make sure that the results are reproducible. Then we set the block size, number of embedding, etc. Here we are getting the vocab size, and finally we set the device. Here Torch would see if you have a GPU. In my case, I have a GPU, so I'll be using that. But if you don't have it, then Torch will fall to use a CPU. If you have a GPU, then that would be great because the training would be faster. But if you have a CPU, then training will take a lot of time. In that case, if you don't have a GPU, then you can go to Google Colab and use the GPU that they give for free. It's a powerful GPU that will help you train the model. Now let's start. Here I'm strangely starting from the head class because it's not easy to go to show you the word embedding layer first because that one will be used in the full implementation. But let's start with the head layer. The head class represents one attention head in a self-attention mechanism. It has three tensors. They are called key, query, and value. These are used to help the head layer understand the relationships between words. The query represents what each word or token is looking for. The key tensor represents the meaning of each token. And finally, the value carries the actual information of each token. You can see that these are linear layers, which means that these tensors are learned during the optimization process. The forward pass works by first projecting the input into these three representations. You can see that we are taking X and projecting that to get K, etc. We get Q, and finally we will get V also here. Then we compute the attention scores, which Andre called affinities. To prevent the model from looking ahead in a sequence, we apply this triangular mask. After masking, the scores go through a softmax layer to turn them into probabilities, and then we use dropouts to prevent overfitting. Finally, the attention weights are used to combine the value vectors, producing the output. As you can see, it's really difficult to explain to you the code without running it. So what you need to do is either run this to basically verify that the shapes are correct, or what you can do is just watch the video that I shared with you here. This one, you can click on this or the links that I shared in the slides to see Andre's video because he explained this very well. And I don't want to spend too much time on this part because what you need to know is the different layers that compose the transformer model. And we have these hyperparameters that we can tweak so that we get to change the size of the model. But I'll do my best to explain this in simple terms. The multi-head attention class extends the concept of self-attention by running multiple attention heads in parallel. Instead of using just one set of queries, keys, and values, it creates multiple independent head instances. We are doing this here. So as you can see, we are looping over the number of heads and instantiating each object independently, and we are feeding that to the module list to be able to run these heads in parallel. And this is exactly what we are doing in the forward pass. You can see that we have this for loop, we are looping over the heads, and we are feeding the input to each head independently, and after that we concatenate the output from each heads. Finally, we project that to we have this projection layer which will project the output of this concatenated tensor into the number of embedding to be able to, as I said before, to link the blocks sequentially. And finally, we use dropout to prevent overfitting because the model will be big, and because we don't have a lot of data, we need to make sure to prevent overfitting. Now we have the block class. This one will use the feed forward, so I'll come back to it. The block layer combines the self-attention and feed forward layers. First, you can see that here we have the self-attention. Basically, it's the multi-head attention class that we explained before. And before applying the self-attention to the input, we are applying normalization. Here you have two choices. You can either apply the layer norm before, or you can apply it after the self-attention if you want. And after applying the self-attention, we will feed the result to the feed-forward network. And here's how the network looks like. It's simple. Here we use the linear layer to make the feed-forward network wider because we want to add more parameters. We want to make the model, we want to let the model learn complex patterns. And finally, we end up with we add a dropout to, again, prevent overfitting. And this is the content of the block. And you will see that in this final class, which is the GPT language model, here we are going to basically assemble all those components to form our transformer model. So let's see. So this is why I did not start with the embedding and position tables, although this is the input of the transformer model, because we added this in this GPT language class, and we had to explain the previous ones before we arrive at this one. So here we have the token embedding table. Let me go to the forward method to help you understand this. So we are going to take the input tokens. Remember, the input tokens are basically, we got them after transforming the sequence text by the tokenizer. So this is the input. We feed this to the embedding table in order to get the associated vector for each token. We do the same thing for positional encoding, and we add them to get the X tensor, which is going to be fed to the other layers. And here, as you can see, we are going to feed that to the blocks. And if I go to the top, you can see that the block is basically a sequential layer that will assemble all the blocks. And here you can see that we have the number of layers. So this will determine the number of blocks to use. So here we are instantiating the block object with number of embedding and the number of heads. And this is exactly what we did here in the forward pass. We are feeding the input to the blocks. So we finished. Now we arrive at the final layer. So here we are applying a normalization before going to the final layer, which will project the output dimension to be of shape, batch size, sequence length, and vocab size. And if I go back, you'll see that this is basically just a simple linear layer that will reshape the last dimension from embedding size to vocab size instead. And finally, we return, let me go back, we return the logits and the loss. From the logits, we can sample the next token, and the loss will help us optimize the weights of the model during optimization. And here, this class has the generate method, which takes the input tokens and the new tokens that we want to generate from this input sequence. So basically, here we are going to get the input, feed it to the model, get the logits. We don't care about the loss, and we will keep appending the logits to the input, and finally return the final layer or the final output with the first input tokens and the new tokens that we generated. Now let's create our model and move it to the device. We are going to use this to calculate the number of parameters. Currently, we have 12 million parameters, and this is not the final value. In the next video, where I will start training the model, I might change this. So this is just to show you that that we don't have any errors while defining the GPT language class. Also, it's a good practice to test the forward pass with a dummy input. Here we are creating, so this, you can see, if I take this, let's run it here, and let's look at the shape of the tensor. So it's 1 by 6. Why? The batch size is just 1. And the sequence length contains 6 tokens. And here we are generating random values that goes from 0 to vocab size -1. So let me delete this cell, we don't need it. And finally, after getting the input tensor, we are going to again give it to the device, because we need to make sure that both the model and the tensors are on the same device in order to do the calculation. And finally, we give the model this input, and if we print this, you can see that we get 1032, and the loss is not because we did not give the model the target tensor. Finally, I have 2 helper functions that will help you print the model layers if you want. So this print model structure, it will print the layers in this tree-like format. Let me click on text editor. So you can see that we start from the token embedding, then we go to the position. Here are the blocks. So this is the first block, this is the second block, etc. And at the end, after the 5th block, we will arrive at the final layer. And you can see also the parameters of each layer independently. You can use this one. Let me run it again. Yeah, it's working. Or use this one, because this one will use pandas in order to generate this data frame. And here it shows you the same thing. It shows you the layer, the type, and the number of parameters of each layer independently. And you can click on these arrows. Maybe you will have a different output. Here I am using an extension called Data Wrangler. Let me search for it. Yeah, I'm using this extension, and I think it helps show the data frame in a nice way. That's all for this video. I hope you enjoyed watching it. In the next one, we will begin training the model, and I'm really excited to dive into that. See you then. Hi everyone. In this video, we will train our transformer model. I will explain the training process, share best practices, and show you how to avoid common mistakes that can stop your model from learning. This video has 2 parts. First, I will go through the slides, and then we will train the model together. Training a neural network follows these steps. First, we use the tokenized data and split it into 2 parts, training and validation. From these, we create data loaders, which feed the model batches of data during training and evaluation. Next, we set the training parameters, like the number of iterations, learning rate, and optimizer. We also save the model regularly, for example, every 100 iterations, and also don't forget to save the model at the end of training. Finally, we evaluate the model and repeat the process, because getting it right on the first try is difficult. Now let's talk about data loaders. As I mentioned earlier, they are used in both training and evaluation, and we can set them up in 2 ways. The first method selects a random batch of data in each iteration, while the second method processes all batches in one iteration. Let's compare these 2 methods with an example. Suppose that we have 4,000 batches in our training set, and each batch contains 64 samples. And let's say that we train for 1,000 iterations. If processing one batch takes about 30 seconds, we can calculate the training time. In the first method, we will take 1,000, multiply it by 1, because we have just one random sample that we selected, and we multiply that by the time it takes to process that batch. This will give us 8.33 hours. In the second method, we will multiply that by 4,000, because we want to process all batches in each iteration. If you do this, then you will get 1,388 days. You see, this is why I showed you both methods, because you need to find a balance so that training does not take forever. The second method is the ideal method because it ensures all training data is used, but it is not practical. I mean, you need to have a very powerful computer to be able to process all that amount of data. The first method is faster, but might not use all data evenly. Some batches will be favored even though we are using random. Some batches are not going to be used. So you need to find a balance. Let's talk about the training loop. You should adjust parameters like model size and batch size to make the best use of your GPU memory. Ideally, GPU usage should be around 90% or more, but not too close to 99% to avoid running out of memory. Here, for example, I have 8 gigabytes on my VRAM. So if I could fill 7.5 gigabytes, that would be great. How do you figure out the optimal batch size that your GPU can handle? Well, it's easy. First, start with a small batch size. If the GPU can handle it, then stop the training and increase the batch size. Keep increasing it until you find the highest batch size your GPU can handle. Also, remember to save the model regularly and monitor the loss. Tracking the loss is very important because it shows whether the model is underfitting, overfitting, or training well. Here in the first graph, we see that the model is underfitting because the loss was not improving and it stagnated, while on the far right, the model is overfitting because the validation loss is increasing. So the ideal situation will be this one. The training loss should decrease over time and the gap between training and validation loss should stay small. After training, test the model by generating text and evaluating the response. If you are not happy with the results, don't worry. Just repeat the process and adjust different settings. This is how deep learning works. It's rare to get perfect results on the first try. You have a lot of hyperparameters that you can adjust, so just repeat the training process until you find satisfying results. During evaluation, check if the model can produce clear and meaningful text. This is the important thing. If the model can produce coherent text, then you are good to go. The model does not need to be perfect at this stage because this is just the pre-training step. The goal here is to make sure the model understands the language you are training it on. Later, we will fine-tune it to make it more useful. Ready? Let's start coding. Before showing you the code, I want you to go to my GitHub repository and pull the latest changes because, as I said before, I am regularly updating the repository. Whenever I make a video, I try to push the notebook and the slides. So please pull the latest changes so that you get these two notebooks. So open notebook for one model training all batches. Both of them are similar. There is just a change in how the data loader works. So let's look at the first one. Here we are loading the tokenizer. Let me run this. We have seen this before, so let's go fast. Here, make sure that the tokenizer, that you train the tokenizer. Here we are loading it. We have the get vocab size to basically give us the size of the vocabulary. And now we are going to create the model. Here I did something else. I have created a script. Inside transformer, we have the model. Basically, instead of putting this in the notebook, I made sure to put it in a script so that we can load it easily. And here we are going to give the GPT language model constructor some variables that it can use when instantiating the model. And this is exactly what we did. So you can see that I imported the GPT language model class from the model scripts. And here are the hyperparameters that I am using. Here I am just showing you the notebook that will train the model. You will see later in the video that I'll make a lot of tries, so I'll change these values regularly. So after creating the model, I am passing it to the device, and this is going to be computed automatically by Torch. So if you have a GPU, we will use CUDA. If you don't have it, then this will fall to use a GPU. So let's run this. And here it shows me that I have a very small model just for demonstration purposes. After creating the model, here comes the data preparation. Let's load the combined text. Remember, we will load this sequence of text and we will use the tokenizer to embed it. And this will give us the number of tokens that we have in the data. So let's wait for this to complete and then I will come back. I am back, and as you can see, we have 618,000 tokens in our dataset. Now let's split it into training and validation splits. Here, first, we are converting the encoded text sequence into a tensor of numbers. So if you want to have 95% of the data as training, then put 0.95. If you want to keep it like this, keep it like this. And here we are splitting the data into training and validation. Let me run this. And here comes the data loader. Here we are using all batches. So here we have this text dataset. We are giving it the data and the block size. The block size controls the maximum input that the large language model can accept. If you set block size to 256, then that means that you cannot feed an input with more than 256 tokens. That will fill the context window and you'll not be able to compute the answer. So make sure that the input stays below or equal this value. Here get item, we will give it an index and it will give us the two pairs, X and Y. And here we will just give it an index and it will add the block size so that I get the input X and I'll predict the next token in the sequence. So this is what get item does. And we are going to use this text dataset inside the get data loaders method. And this one will give us both the training loader and the validation data loader. So let's see how this works. Here we are creating two instances of the text dataset class, and here we are giving it the training data as well as the block size. And here you can see that we are moving the tensors to the device. After getting the training dataset, we can create the data loaders. You give it the dataset, the batch size, and shuffle. Make sure that shuffle is equal to true so that you randomize the data. We are doing this just for the training because this will be used to optimize the model, whereas in the validation data loader, this is set to false because we are not going to use the validation data loader or the validation data to optimize the model. We are using this just for evaluation purposes. So run this, and here we can test this just to make sure that it is working. So we are getting the training and validation data loaders from the get data loaders method, and we are using the next method to basically get a batch. And after printing the shape, here the batch size is 128, while the block size is 512. So let me run this. Okay, so it is working. Great. We arrived at training. So here, first we want to estimate the loss. This is going to be used in order to plot those loss curves that we have seen in the slides. So first, put the model in evaluation mode because we are not going to compute gradients. Then for each split, so we are going to do this for both training and validation, we are going to compute the loss. And here, because we have, so here we need to evaluate this integer that I called evaluation iterations. Why? Because we don't want to go through all the data, through all the batches that we have in the validation set, because this will slow the training process. We just want to get a sample from the validation data and run the model on it and get the loss value. So what you could do, if you want to have the validation be computed on all batches in the validation data, then remove this and calculate the loss on all batches. But if you want the training to be a bit faster, then add this value and provide it to the estimate loss method. So we are calculating the loss for each batch, and after that we are calculating the mean. Finally, before leaving, make sure to set the model to train, because we are going to resume training. And finally, we return the loss that we put in the output dictionary. So make sure to run this cell. Here, save checkpoint. So this is very important because let's say that you are training the model for 10,000 iterations and something malfunctioned and the training stopped for some reason. So at least you have saved the model multiple times during training. So don't wait until the last iteration to save the model. No, make sure to save it regularly during the training process. And here, basically, we are using the save method from Torch to save the checkpoint. Here we are saving multiple things. So we are saving the epoch, the state dictionary. This is very important for both the model and the optimizer, and the last value for the loss. So run this. And now here comes the training loop. So as you can see, I already done this, but let's see how it looks like. First, we have some parameters that we can tweak. The number of iterations. This is the epoch, so I have called it iterations. Evaluation interval. So this means for every 10 epochs, we are going to use the estimate loss function to compute the value. This is what we are getting here. So you can see that in the first iteration, we computed the loss. After 10 iterations, we are evaluating the model, and so on. So this is what eval interval is used for. Eval iteration, as I told you, it's going to be used by this one, basically to limit the number of batches that are going to be used to calculate the loss. But if you don't want to use this, then remove it from the estimate loss function entirely. The learning rate will be used by the optimizer, and here we are using Adam. Finally, we are getting the training and validation loss again, data loaders again. Here we have two arrays to keep track of the loss during training so that we can plot it down below. And now we start. So for each iteration and for each batch in the training data, because this one is all batches, so we need to use all batches in the data in each iteration. And this takes a lot of time to complete. First here, this one is just for evaluation, but let me collapse this and start with the training. So you give the model the X and the target. It will give you the losses, basically the probabilities. Here you compute the gradients and perform the optimization. After that, in this block, we are going to evaluate the model. So if this condition is valid, we are going to use the estimate loss function, and we are going to append the loss for training and validation in these two lists. And we have this print statement just to print this so that we can see the values while the model is training, and to intervene. If we see that the validation loss is starting to go up, it should be safe to stop the training because the model is degrading, it's not improving. And finally, we save the model after in each iteration. So if I close this, you can see that when I finish working on all the training batches, I will save the model. After training, I have this so that I can plot both training and validation loss. And as you can see, the model was doing good, but I stopped it because I was just creating the notebook. But this is what you should see when training the model. Both train and validation loss should go down over time, and the gap between them should be minimal. Finally, here, if you want to test your model, you can basically give it an input and use evaluation again. We don't want to compute gradients, and use the generate method. And finally, decode tokens so that you get the text back. So this is similar to what we have here, but if I scroll down to the data loader section, you can see that it is very simple. You are just going to get a split. So do you want to get the training split or the validation split? And we are going to use that to get the data. And finally, we are going to basically get a random index with source.random integer and get X and Y and use that in the training loop. So if I scroll down to the training, you can see that the estimate loss is the same. Save checkpoint is the same. But here, you can see that, let me collapse this. This time we are iterating just over the max iterations. There is no need to iterate over the data loader because we are getting random batches each time. So here we use the getBatch method, and because we are training the model, we will use the training split, and this gives us X batch and Y batch, but randomly. So here, this one is faster, but you will run into issues because sometimes some batches are not going to be used in the training because this is a random process. So you need to increase the number of max iterations so that you make sure that the random process will use all the batches. So basically, this is the only difference between the first and the second notebook, but the rest stayed the same. So here we plot the losses and we generate from the model. So this is what I wanted to show you in the first part. In the second one, I will start training. I'll start playing with these hyperparameters and see if the model will learn the Darija language, and hopefully it does. And then if this works, and I will show you that this is not very easy to get the model to work from the first try, but I'll show you how to follow the process that I showed you in the slides to get good results. So I started training the model. I kept the first hyperparameters like this. So that gave me a model that contains 0.5 million parameters. This is very small, and I think the model will underfit, but let's see. So I kept these things the same, and when I came to training, you see that the model was doing good. So the loss started at around 6.9, and at the end it reached 4.7, and the gap between the training and validation loss was very small. So here we have 4.7 and here we have 4.9, so 0.2 difference. It's not that big. And if we plot the training and validation loss, you can see that the loss was decreasing steadily, but you can see that it stagnated and it will not go down. And this is very similar to the plots that I showed you in the slides. And this shows that the model is underfitting. And we were expecting this because the model is very small. We have a lot of data, so the model is not able to learn more. What we should see, if we increase the model, this should decrease. So the loss should decrease maybe to around here. It will also stagnate. After that, we will increase the model size even further and see when the model will overfit. So at a certain point, the model will be so big because we have a small data set, the model will overfit that data. Let me do another run. This time I will change the hyperparameters to increase the size of the model, and I'll come back. And I forgot to say that I am using the random batches approach because this one is faster to train the model. But later I'll go back to the all batches method and try it out also. And before I finish this part, I also want to say that when I generated some tokens from the model, I see that it isn't good. And this matches what we see in the training loss. The model didn't learn a lot from the data. This is why the generation isn't that great. Here are the results from the second training run. And as you can see, again, the model was underfitting. If I put this here and the first run here, you can see that they are similar, but here the loss was lower, but you can see that the loss stagnated. So that means that the model did not improve a lot from what we did before. Also, the generation wasn't that great. And here the model is 3 times bigger. So here we have 1.5 million parameters, but because the number of players is just 1, that means that we don't have a lot of parameters. So the model will not be able to learn a lot. So what I will do now, I will increase this to, let's say 3. Let me see how this will give me 3 million parameters. So let's increase that to 4. And also something very important is the embedding. I'll change that to 768. This will increase the size of the model a lot. Why? Because so this means that each token will be represented by a vector of size 768. If the vector is big, this means that we will store a lot of information for each token. And this is why the size of the model jumped a lot to 30 million. So now let me see. So I'll also decrease the batch size because the model will take a lot of memory if I try to load it on my GPU. So let's just do this. Let's use 30 million. Here we have 4 layers, the number of head. So this will not change the parameter size. So you can see that it does not change it. It will just have multiple heads. The block size controls the max input. Dropout, this one is used for overfitting. So I'll just decrease this to 512. So this will give me 30 million. And then I just want to go progressively just to see if the loss will go down. And if the model still doesn't have a lot of parameters to learn more, then I'll keep increasing the embedding size. So I'll keep this. I also want to show you that the checkpoints are here. So make sure to create folders inside the output folder so that the checkpoints are saved correctly. So this is great. I'll just duplicate this because I want to keep those graphs just to show you at the end how those parameters affect the model training. So let's call this tree. Here I have block size 512. I think these are enough. So now I'll just go back to this one. Let me show you what I have here in Ghosty. You can see that the model was taking 6 gigabytes before. So I'll just free the memory, restart the notebook. As you can see, now we freed the memory. Here I am using OBS to record. This is why I am using a little bit of memory. Let me close these because I no longer need them. And here, so I'll keep these parameters. I will go down to the training loop and I want to change some things. So here I will change the learning rate to 3e-4. I want to increase it a little bit. I want to keep the max iterations to 1000. And here I need to make sure to change the folder to run number 3. This is the third run. I forgot to save the second run, but that doesn't matter because the model was not great. So let me create the new folder and everything should work. So I'll train the model and I'll come back. I have finished the third training run. Here is how the training and validation loss functions looks like. I have copied both images from this run and the previous one, and I have them here in Inkscape just to see the difference. You can see that both of them started at a loss of 7, but then you can see that here we quickly reached 4.9. In the previous run, that took us 40 evaluation steps, so that took us a lot of time. So with this big model, we were able to decrease the loss quickly, but after that, the loss stagnated again. What I will do now, because increasing the size of the model did not help, so I'll stop using the random batches approach and use the all batches approach. This one will take a lot of time, but what I will do, instead of having 100 iterations, I'll just keep 1 iteration, and here I'll loop over all the batches, and hopefully this one will work. So I will name this run number 4. Let me go back, or first let me go to the previous notebook. I need to free the memory. So let's click on restart. I'll close this. I'll go to the top, and here let me change some values. So I'll keep the batch size small. I'll use 32. Here the block size, let's make this small to 56. The embedding size, I'll use 512 for now. Let's increase the number of layers to 6. Let's see what this will give us. So this gives us 20 million. This is big. So I'll decrease the number of heads to 6. Oh, that's increased the value. I don't want to decrease the number of embedding or the embedding size, because if I decrease this, yes, the model size will decrease quickly, but I want to have a sort of big embedding vector for each token. So let's keep this as 512. I'll keep this to 6 layers. And here I have to decrease the batch size to, I think, 16 or 24. So let's try 16 first and see if this will fit. So currently we have 20 million parameters, or actually let's try something. I'll decrease the number of layers to 4. I'll keep the batch size 32. We have 13 million parameters. This is exactly what we had before. And now let's train this just to see if the loss will decrease or not, because it stayed at 4.7. So I would like to see the loss keep going down, because this is underfitting. It's not, the model is not learning from the data. And my assumption is that by using random batches, that did not help our model. So let's give the model all the batches and see if that will help it generalize better. So I'll run this training run and I'll come back with the new results. This is the 4th run, I guess. I have finished training the model for the 4th time, and as I said, this time I used all batches. This method is really awesome, and I think it's the one that we should use from now on. Why? Because let me show you. So the model stayed the same. This is the size, it's 13 million parameters. We encoded the data. Here is the data loader. So this time during training, we were iterating over all, where it is, here it is. We were iterating over all the batches in the training loader. And as you can see, because I have a lot of data, here I have 8,700 steps almost, and the training loss was doing good. Let me show you the graph. It looks interesting. If you remember, in the slides I showed you that if you see this, this means that the model was overfitting. But this is exactly what we need. I mean, you will be confused right now. Why are you saying this? Let me explain. First, the loss that you see here was not computed over all batches in the training dataset or in the validation dataset. Remember, if I go back to estimate loss, you see that we have this variable that controls how many samples that we take from the data loaders. If you want to get the accurate loss value, you should remove this. I said that this will increase the training time, but this will give you the actual values. I kept this just so that I don't slow down the training. But if you estimate the loss every 100 epochs, that will not cause a lot of problem. So it's safe to remove these if you want. Also, let me go back to the training, to the graph. You can see that here, let's say that evaluation iteration, that variable was 200. And I have more than 8,000 batches. And you can see that I have just one iteration. I intentionally set max iteration to be 1. And I just went over all the training samples and optimized the model. So those 200 samples, the model has seen them just once. So it did not overfit on those samples. So you can see that the training loss went down, but it doesn't mean that the model saw those 200 samples more than once. It has only seen them once. And this is promising. It's really awesome. Here, the validation loss was going up. Why? Because let me go back to how we split the data. So you can see that here we used the index. So whatever comes after this, we will take it as a validation data. Here comes the problem. My model is not a model like ChatGPT or Gemini or the other general models. So those are trained on the whole internet and they are expected to know everything because those are general models. So if you have, for example, coding samples in the training set, you should have coding samples in the validation set. But my model is simple. It is trained just to learn the Darija language, but specifically to mimic me or another person. So here, my dataset contains conversations between me and other people. We could have in the validation set conversations between people that are not split between the training and validation set. So this is why what we might see in the, let's say that during training, I was talking with people about, let's say, programming, computer science. But in the validation set, I was speaking with people about, let's say, football and something else that is not related to the training set. The model will not be able to generalize. Why? Because in the training set, we have just samples that are related to programming and computer science. So this is intentional. So I wanted the model to be able to learn from the data as much as possible and to be able to model the Darija language. I will also experiment with removing the validation dataset and keep one data, give it to the model and see at the end if it is able to learn the Darija language. And let's go and see the generation. So here, excuse me if you don't know the Darija language, but those that understand it, people from Morocco or Algeria, will see that the model is generating good text. So here, let me see. So this is the input sequence. You can see that it is here. And after that, these are tokens that the model generated. You can see that it generates emojis. This is how we laugh if we speak with other people. We keep pressing H. It's funny, I know. What else? So let's see. I'll change this. To say hello, we say salam, salam labas. So this means hello, how are you? And let me see what the model did generate. So salam labas alik, hello, how are you? Hello, Imad. So as I said, people from Morocco or Algeria will understand the text. It is not perfect, but the model is using, I'll say, correct words. It's not using just, random words like it was before. Actually, let me go and open the notebooks that we started with. This is the first try. If I go to the generation, so this is the text that we got. It's completely nonsense. So for those that understand the Darija language, we'll see the difference. Let me put them side by side just to see. So here is the before and here is the after. It actually worked. So this is why I said that if you see this, it does not matter. In the slides, I showed you that this is bad behavior because the model will not generalize. And this is true if you are training classifiers, those classical models. But with LLMs, you want the model to learn as much as possible. Because don't forget, this is just a base model. Here is just completing the text. The conversation is not meaningful. It's not coherent. But don't forget that we have a fine-tuning step. We will take this model and fine-tune it on a conversational data so that the model is able to mimic me or other person. I'm really excited, and in the next episode, I will show you how to form that dataset, and after that, we will start fine-tuning the model. See you next time. Hi everyone. In this video, I will talk about how to create the fine-tuning dataset that is used to train the base model further on a specific task in order to create an assistant. Let's see the details. As I said, this dataset is used to teach the base model to be good at a specific task. In our case, we want this dataset to teach the model to mimic the way a person talks. You remember the special tokens that I talked about briefly in the BPE video? We will use them in this part. The raw data looks like this. We have a back and forth conversation that we exported from WhatsApp. As an example, this data will be converted to this format. We start with the start of text token, and then we put the role, in this case user. We put the separator token, and after that, we put the user message. And finally, to finish the turn, so this is the user turn, we add the end of text token. And we repeat the same thing, but this time for the other person that talks, that responds to the user's answer. We will consider this as the answer that the assistant should produce. We repeat the same process for the rest of conversation, and at the end, we form our fine-tuning data. Here I want to highlight the user and assistant roles. So here, if you want to switch, let's say that the user is the other person that I'm talking to, and the assistant is me. So if I want the model to mimic how I talk, then I'll put all my answers in the assistant section. But if I want to mimic the other person that I'm talking to, then I'll put the answers for that person in this section. Something that you need to keep in mind is that this dataset does not need to be big like the pre-training dataset. So it means that you can generate high quality data manually, and this will help boost the base model to train very well. Let me show two examples of how to form the fine-tuning dataset. Here is the first, and let me show you the second one. So we have the two examples in front of us. Do you see a difference? In the first example, we have one message from the user and a reply from the assistant. And we consider this as a single example that the base model will be trained on. On the other hand, in the second case, we have multiple turns between the user and the assistant. So what's the difference? The difference is that in the first case, we have no context because we have just one message and a reply. And that reply, if we want the model to understand how to reply well, then it needs to know the context. And in the second example, we have a clear context because we keep the history of the conversation. But if you want to use the second example, make sure that when forming the dataset, that the input should always be less than the block size. This is where the block size comes into play. In the previous section where we trained the base model, we have fixed the block size to a specific value. So if you want to use the second approach, this will consume a lot of tokens in the input, so you could easily exceed the block size value. So keep that in mind when creating the dataset. And here I'm saying, think of showing the model multi-turn examples because this will help it a lot to understand how to reply to a user. In this series, I will use both approaches. I'll start with the first one because it's the simplest, and then we will evaluate the model to see if it will be able to reply to the user. It should be able to reply to common messages that are available in the fine-tuning dataset. But if you want to discuss with the model on topics that are not in the dataset, then we will have a problem. Also, if we want to have a coherent conversation with the model, that will not work. Then we will go to the second approach and see how this approach will solve those issues. Are you ready? Now let's code. Open the 5th notebook. It's called Fine-Tuning Dataset. And here we will start by reading a conversation that we exported from WhatsApp or Signal or any other app. Here I added a dummy data just to show you what it contains. Let me show you. So basically it's a conversation between two people, and I generated this with ChatGPT. This is fake data. Let's see how we will use it. In that dataset we have, or in that conversation we have 75 lines. And the first thing we will do is to clean the conversation. We have done this in the first notebook. So here we are going to apply the same filters that we applied in that episode. So nothing new here. And after that, we will see how many lines we removed. In this case, we will not remove any line because this data is clean. In this section, we will see how to create the dataset. First, we need to group messages by sender. If I open the dummy data again, you can see that sometimes a person can send multiple messages sequentially. This is not ideal. So we need to concatenate those messages in order to have this structure. So as you can see before you, we have user 1, user 1, user 2, user 2, and then we have user 1. What we would like to have is like this. We want to have user 1, user 2, user 1, user 2, etc. So in that case, we will just concatenate the strings or the messages and add a new line character between them. This is how it looks like. And this is exactly what we will achieve with this code. So remember, we had 75 lines after assembling those, or after grouping the messages by sender. Now we have only 65 entries in the data. So after doing this, now we need to convert the messages into this format. You can see that we start with the start of text token, then we put the sender, we add the separator token, we put the message that the person has sent, and finally we finish with the end of text token. And this is how we are doing this. So we are defining the special tokens, and then basically for each message entry, we are going to extract the sender and the message and form the input sequence. And finally, again, we will have 65 tokens, but this time, if I look at let's say the first entry, you can see that this is what we have. We have start of text token, the first person, the separator, and here you can see that we concatenated the two entries into just one. Here we have hey, we have this new line character and the second message, and we end the sequence with the end of text token. So after doing this, we are going to save the data in a JSON format so that we load it in the next notebook where we are going to train the model using this fine-tuning dataset. So make sure to run this, and let me do that. Let's open the data, and here is how it looks like. We are using JSON because it will be easier to parse than saving it as a text file. So that's it for this video. As I said, in the next one, we are going to start the fine-tuning process. I'm going to start without providing the model a context, and after that we will try to modify the dataset so that we provide the model with the context, and then we will compare the two approaches to see which one delivers a good assistant at the end. See you next time. Hi everyone, and welcome to this new video where I will talk about fine-tuning and how it is used to create an assistant from the base model that we trained in the pre-training episode. I will also show you the different methods of fine-tuning that you should know before attempting to train the base model further on a fine-tuned dataset. Fine-tuning is the additional training performed on the base model to create an assistant that excels at a certain task. We have two main methods of fine-tuning. The first one is called full fine-tuning, or if you do some research, you will also find people call it instruction fine-tuning. How does it work? Well, we take the base model and start tweaking all of its weights. This is why we call it full fine-tuning, because we are going to modify the full model. In the second method, which is called PEFT, which stands for parameter efficient fine-tuning. Here in this case, we don't train the base model. Instead, we freeze the weights from the full model and we add other weights on top of it. This is what I illustrated here with these new blue neurons. This method is performed with LoRA or QLoRa. LoRA stands for low rank adaptation, and basically QLoRA is LoRA but in low precision because Q means quantized. At the end of training, we get something called an adapter, which basically stores the new weights that we attached to the base model. And the cool thing about this is that we can detach and attach different adapters to one base model. And each adapter could be specifically trained on a, let's say, specific domain so that the model excels at that specific task. Now let's talk about efficient training. Training on one example at a time is not efficient. Why am I saying this? Let's look at this example. Here is the first input. Let's say that it contains 43 tokens. Look closely. Here, this input contains two things. It contains the user message and the assistant answer. In the second example, we have multiple turns. So we could have user assistant. So basically the length of this second input is bigger than the first one. And here let's assume that we have 86 tokens. This is a problem because you can't batch these two inputs because they don't have the same sequence length. Here we have 43, but in the second example we have 86. If you don't think of a solution to solve this issue, then you will end up training the model on each example at a time. And this is why I said in the beginning that we should not train on one example because this is inefficient. Luckily, there is a solution and I will show it in the next slide. As I said, ideally, we want to batch the data. But how do we do that? The solution is to use padding tokens. This is a special token that is used to create sequences with the same length. Let's look at the same example. Here we have the two different inputs. Let's assume that the block size is equal to 256. First, we encode the first input. We get this list of tokens. Then we do the same thing for the second input. Now, we add padding tokens to each sequence until they all reach the block size. Notice we added the padding tokens to the end of this sequence of IDs, but we can also add them to the, let's say, to the start of the sequence if we want. Both options are valid. And this is how you use padding tokens to batch the data, making training faster and more efficient. I want to emphasize something. The padding tokens are not considered when computing the loss function because the model should not generate the padding token and it should not see it during the fine-tuning process. Basically, we are using the padding tokens as a mean to batch the data in order to make the training more efficient. Let's see how we form the X and Y pairs. And this is simple. They are formed like the first stage. The first stage means pre-training. We start with a sequence of text. We encode it with the tokenizer. Then we add the padding tokens to the front or the end of the sequence of IDs. We take that sequence and we consider it as the input, which is X. Then we shift the sequence by one position and we consider that as the target. Notice we have a problem. We are trying to access a value that does not exist in the list. To fix this, basically, we will just append another padding token because we don't care about the last value. We keep repeating this for the rest of the sequences and then we create our data loaders. Now let's see how to implement this in the notebook. Here is the notebook. It's called 6.1 fine-tuning with no context because I will create another notebook but with context. And if you watched the video where I talked about the fine-tuning dataset, I explained what no context and what with context means in details. So let's start. First, we need to prepare the data. In the previous notebook, we have stored the fine-tuning data as a JSON file. So let's start by loading it. And to make sure that it was loaded correctly, let me print the length of the data. And here in my example, I have 7,700 examples. That's good. Now let's load the tokenizer. And here I will load a different class. Instead of using the basic tokenizer, I am going to use the regex tokenizer. It's similar. If I use the load method, I will be able to load my tokenizer, even though it was a basic tokenizer. The difference between basic and the regex tokenizer is that this one will take care of the special tokens when we encode the sequence. The basic tokenizer does not take that into consideration. So let's run this cell. And now let's start tokenizing the sequences. So we are going to loop over the sequences and then we will use the encode method. And here, because we are using the regex tokenizer, we are going to add this parameter, and this basically allowed special. It will take care of those special tokens. If you want, you can see that here, this parameter accepts different values. We have none, non-raise, etc. But we don't want to raise any errors. We just want to encode those special tokens. So let's do that. And here, for example, the first sequence contains 66 tokens. Now let's split the data into both training and validation sets. Here I'm going to take 95% of the data as training, but here we have to be careful. When separating the data into train and validation sets, we need to make sure that we keep the sequence, or that we keep the conversation form. So we should have person 1, person 2, etc. In the training and validation sets, we should always start with the first person, and then at the end we will have the assistant message. If you take this index randomly, then this is not guaranteed to happen. So we need to do that manually. And first we are going to get that initial index. Here we have a while loop. We are going to subtract 1 from that index until we find that the last message contains the assistant turn. If we find that, then we are going to stop, and then we are going to split the data. And this will guarantee that the last message in the training data will be the assistant turn, and the first message in the validation set will be the you message, or the first person's message. If I print this, you can see that this is correct. So here is the training set. This is the start message. You can see that the first item in the training data is the U-turn, and the last message is the assistant message. And in the validation set, it's the same. So we start with the U message and we end with the assistant message. After doing that, we are going to get the training data and validation data. Here, this is text, but we don't want that. We want to split the tokens. This is why we are using the tokenized data lists instead. And now in this section, we need to combine the U and assistant turns into one sequence. Previously, each item in the data contains either the U turn or the assistant's turn. But what we want is that we want to combine those into one item, into one sequence, and create a new data from that. And this is exactly what the combine turns method does. It will take the data, and here, sometimes if we group the two items, we might exceed the block size. So if we set should trim long sequences to true, then we are going to trim those sequences to not exceed the block size. So let's see how this works. Basically, we are looping over all the items, and here we add -1 because we are indexing 2 items at a time, and the step will be 2. So we take the U message and the assistant message. If for some reason they are null, they don't contain anything, we are going to skip that. But if that's not the case, then we are going to combine them. And here, if the length is greater than block size and this flag is set to true, we are going to trim the final message. And after that, we are going to append it to this list, and we are going to return it. Okay, so let's print the length. Remember, before we used to have 7,383 items in the training set. But after combining the U and assistant turns, now we basically have 3,691, and this is half of the previous length. And the same for the validation set. So that's correct. Let's keep going. Now let's convert each sequence of tokens into a tensor. So this is the problem that I talked about in the slides. If you try to do this, then PyTorch will give you an error. Why? Because each sequence contains a unique sequence length. So let me take this just to show you what I mean. So if I take the first item and then okay, so let's take the last item. You see that the sequence of the first item is 104, but the last input in this list contains 56 tokens. When you use torch.tensor, PyTorch expects that all sequences have the same length, but this is not correct. This is why it gives you this error. So we need to make sure to add the padding tokens to solve this issue. So the padding token here, I chose -100. This one is used as a mask. We are using -100 because the categorical cross entropy loss function, when it sees this value, it will not take it into consideration when computing the loss value. And this is exactly what I said in this comment. Okay, so let's see how we apply the padding to the data. So here we are going to using it for both the training and validation sets. And it's simple. So it takes the data, it takes the block size and the padding token. Now we loop over all the items. We convert the list of tokens into a tensor, and we use the pad method, which comes from the functional API. We give it the tensor, and here, if you want to use right padding, you keep this. If you want to use left padding, then you use the second value. So here, basically, we are going to compute how many values are missing from the tensor. And based on that value, the pad method will basically add those padding tokens that are missing to basically have all the sequences be of size block size. This is simple. So after getting the padded tensor, we are going to add it to the tensors list. And after that, we are going to stack them. And using the stack method, we are going to basically create the batch. So now we use the apply padding to data method for both splits, and let me run this. Okay, so you can see that this is the batch. So the batch size is 3691, and you can see that all sequences have 256 as the sequence length because we used the block, because our block size was set to this value. Let's look at the first element in the training data tensor list, and you can see that here we used left padding. This is why we have the padding tokens at the start of the list or at the start of the tensor. But again, if you changed this and used the other one, then you will add them to the right of the sequence. And the same thing for the validation data tensor. Now let's create the data loaders. I would remove this cell because we don't need it. Okay, so here is the fine-tuning dataset class, and here it takes the data, the device, and the padding token. And it's simple. So if you go back to the slides, I showed you that basically X is the sample. We take all the IDs and we consider that as the X. But for the target, we are going to shift the positions by 1 and take all the tokens. But we have a problem. Here the shapes won't match. This is why we are going to add another padding token to the target. And after that, we just return the 2 pairs. And here we have the batch size, the device. If I run this, then I should not get any errors. But let me comment this just to show you that we will have a mismatch in the sequence length. Here we have 256, but here we have 255. This is why we need to add another padding token to the end of the target tensor. Now if I print this, you can see that we have 256 in both X and Y. Now let's start fine-tuning. We created the data, we prepared it, we did everything. So now we are going to start by loading the saved checkpoint. Here we are, so let's just create the instance of the GPT language model class. In this case, I have 13 million parameters. And here I will load the state dictionary from this checkpoint. And here it says all keys matched successfully. So if you changed the values here and try to load the checkpoints, this will not work. So make sure that the values are the same so that you will be able to load the model or the checkpoint. And here I can generate from the base model just to make sure that those weights are correct. I won't do this, I will skip it. The estimate loss function is the same. I have removed evaluation iterations. That parameter is no longer passed to the estimate loss function. So here I will estimate the loss on the full data instead of just a subset. So let's run this. We have these saved checkpoints. It did not change. And here is the training loop. It's similar again. Here I have decreased the learning rate because we already trained the base model. I want to fine-tune it smoothly. I don't want to fine-tune it with a high value of the learning rate. Here I want to evaluate the loss each 20 iterations, and the max iterations, which is basically the epochs, is set to 20. But you can play with those values. After that, we are going to print the training and validation losses. We are going to plot them. Sorry, we are not going to print them. And finally, we have this method that will basically generate from the model. And here we have a difference. Before, we used to basically generate, let's say, 100 tokens if we want, because the base model does not know where to stop. But because the fine-tuning dataset contains the end of text token, then the model, if it wants to stop, then it should generate this token. So here what we do, basically we create a while true loop. So this will loop indefinitely, and in each iteration, we will generate one token at a time. And if we detect that the model generated the end of text token, then we are going to break from this while loop. So this is the only difference between this generate functionality and the generate functionality that we had in the pre-training step. So I showed you the notebook. As I said, this is no context because we take one user message and one reply and consider that as the input. But after training the model on this first case, I am going to create another notebook where I will provide more context. So instead of taking just one user message and one model answer or one assistant answer, I might take 2 or 3, depending on if I could fit that into the input. So now what I will do, basically I will repeat the same thing that I did when I pre-trained the base model. I'll try running this multiple times, and whenever I finish a training run, I will show you the results and generate from the model to see if this is a good training run or not. And it depends. If this video is long, then I'll just talk about the no context version, and I'll leave the context version to the next video. If it isn't that long, then I'll make sure to merge them both into one single video. Now I am ready to start training the base model. Here is the training loop, and I will start, as I said, with a small learning rate. I'll train this for just 5 epochs. I'll evaluate the model every 20 iteration. Let's run this just to make sure that it won't break. Okay, good. So the model is now fine-tuning. When this finishes, I'll come back and I'll show you the results. I am back, and as you can see, the training finished. We can see that in the first iteration, the loss was around 9.7, but at the end of training, both the training and validation loss went down significantly, and that's a good thing. Let's plot the loss, and this looks good. If you remember, in the pre-training notebook, we saw that the training loss went down, but the validation loss went up. And in the slides, I showed you that's a sign of overfitting. And I said in that episode that I don't mind if the model was overfitting, because in the validation set, we did have a different distribution. So it's not fair to test the generalizability of the model because we have a small data set. But this is what you should see when you train a model. Because here I took a conversation between me and another person. The dataset, the distribution will be the same. Yes, there will be a difference sometimes, but that's acceptable. So this is why the curves are looking great this time. So over 5 epochs, so you can see that here the loss is starting to stagnate, but the loss is not going to tell us if the model is able to generate good answers or not. We need to test this with the generate method. So here I am starting with this sentence. It says, "Hello, how are you?" Here, let me collapse this. I'm going to print that message as the U-turn, and after that, when generating the model answer, I'll print it too. So let's do that. Okay, so here, the first thing that I see, the generation is not that great. But I see that the model was able to pick up that it should use the end of text token in order to finish the sentence. But here, if I keep generating from the model, I'll see that sometimes it will give me good answers. Yeah, for example, here it says it answers, but I mean, this is not a good answer for this specific message that I typed. Maybe the generation is not that good because we trained the model just for 5 epochs. So let me keep generating just to see. So you can see sometimes it does generate long answers, but currently the generations are not that great. So let me do the training again, but this time I'll train it for more epochs. Also in this second training run, I'll try to increase the learning rate from 6e-5 to 1e-4, and the max iterations, I'll increase that to 10. Let's train the model and see if this training run will be better. I am back, and the second training run finished. Took me almost 8 minutes. If we plot the training and validation loss, you can see that again. This is what we saw before we trained the model for 5 epochs, and we saw that it started to stagnate. And here we start to see a little bit of overfitting, but it's not that bad. Again, let's generate from the model to verify if the generations are good. Okay, so this time I changed the sentence, and the model is generating text that is understandable. The answer is not correct. It means that this is not an answer that you will say to this specific user message. But what I'm looking at here is the model able to generate coherent text. But here I was generating a lot, so here it starts laughing. So yeah, definitely the model is not you can't have conversation with the model like this. I'm assuming that because we use no context, the model is not able to learn how to converse with the other person. But what's great about this is that the model knows that it should respect this new format, and it should generate the end of text token in order to finish the conversation. But as I said, if I keep generating, sometimes I get good results, but it's very rare. I'm not going to stop here. I'll train the model even further. So instead of 10, let's train it for 20 epochs, or let's go up to 100. Let's have this final training run to be exaggerated. I just want to see, even if the model overfits the data, I just want to see if it will at least give us average answers that are related to the question or to the user message. So I'll do this third training run and I will come back. This training run took 100 minutes to finish. And if I plot the training and validation loss, you can see that we get the same behavior that we saw in the pre-training episode. This clearly indicates that the model is overfitting, but at least let's see what it will generate. Sadly, the results don't look great. What I observed is that the text is okay. The model knows how to use words together in order to form coherent sentences, but the answers of the assistant to the user queries are not related. That's not great. There is no problem with that. The good thing is that we have a notebook that allows us to do the fine-tuning. Later, we will change the hyperparameters in order to see if we can get a model that converts very well. I will stop fine-tuning this model with the no context approach, and now I will create the other notebook that will allow me to create inputs with context, and let's see if that approach will be better. Here is the second notebook that I called 6.2 fine-tuning with context. It's similar to the previous one, but let me show you what I changed. But before that, let me run these cells so that I can prepare the data. In this cell where we combined the U and assistant turns into one sequence, we will take this output and feed it to the merge conversation turns. The merge conversation turns method is simple. It takes the combined data that we got after applying the combined turns method, and it will try to take multiple sequences and merge them into one big sequence, but we need to make sure that the new sequence does not exceed the block size. So let's see how this works. The new data is basically the new list that we will get at the end. Current sequence is a list that we will use in order to merge multiple turns or multiple sequences. So here we are looping over the combined data. We get the first sequence. If the size of the current sequence plus the new sequence that we got, if this is smaller than the block size, then we will append that sequence to this list. This is a temporary list that will allow us to combine the sequences. In the next iteration, we will get another sequence. If this condition is always true, we will keep extending the list. But let's say that this condition is no longer true. Then in the else block, we will make sure that we have something in the current sequence, and then we will append the new sequence to the new data list. And after that, we will refresh the current sequence with the new sequence that we got. And we will keep doing this until we reach the last sequence. And we need to make sure that if there are some sequences that were not added to the new data list, to add them at the end, because this condition might be true at the last item, and if it is true, then there is no way to add that sequence to the new data list. So after running this, you can see that after comparing the length of the combined trained data and the merged trained data, we can see that it is much smaller. It's 3 times smaller than the original data that we had before. Okay, so let's continue. As I said, this is the only change. The rest is the same. So this will not work because we don't have the same sequence lengths, but we will add the padding token. But here we need to make sure to, instead of using the combined training data, to use the merged training data and merged validation data instead. Okay, let's look at the tensors. You can see that this time we have fewer padding tokens because we merged multiple sequences. Let's create the data loaders. Let's verify that the shape is correct. Yes, it is. Here the batch size is 64, but because we have few data points, let's decrease this to give the model few samples in each iteration. I mean, if you want, you can increase the batch size as long as it fits in your GPU. And now let's start the fine-tuning. First, let's load the model. Let's load the checkpoint. Let's skip the generation. We don't want to do it. Here we have the estimate loss function, save checkpoint, and now let's start the training loop. Let me start small. I want to set the max iterations to 1. The learning rate, let's set it to 1e-4. Let's evaluate the model every 20 iterations. And as I said, the rest will be the same. Just make sure to create the folders here because this is the first run. So I'll change this from run 3 to run 1. So let me run this and I will come back. Training this model was quick because we have just 1 epoch. Sadly, I don't have a lot of points because the interval was higher, so I needed to decrease it to get more points because now we have few batches than before. And now let's start generating from the model. Okay, so as you can see from this generation, it doesn't look good because we trained the model for 1 epoch. And here I added break because the model was not generating the end of text token. So I had to add it manually to force it to stop when it reaches the block size. So that was expected. Now let's train the model for more than 1 epoch. The second training run has finished. This time I trained the model for 10 epochs and I have changed the interval for evaluation to be 5 instead of 20. Let's plot the loss functions. They look good. And now let's generate from the model. So now there is no need to break manually, but I'll keep it anyways, because now the model, since it trained for 10 epochs, it knows that it should generate the end of text token. So I changed the prompt to be, hello, how are you? Have you seen my last video? And the model answered by saying yes. And here it also added this laughing emoji. But you see that, yeah, it works, but it's the same behavior. But I had to test more just to make sure to see if this approach is better than using no context. But from what I can see, that the generations look great. The model generates good text like before, but the answers, yeah, so as you can see, sometimes the model generates few tokens, sometimes it generates a lot of tokens. I will do another training run. This time I'll train it for 20 epochs. I won't go to 100 because that will the model will overfit. So let's do 20 and here I'll do 3 e-4, or actually let's keep it 1 e-4 because since we added more epochs, then we should, instead of increasing the learning rate, we should decrease it. So let's keep these hyperparameters and let's hope for the best. I will train the model and I will be back. I am back, and as you can see, the model trained for 20 epochs. Let's plot the losses. Again, we get the same plot each time, and whenever we increase the number of epochs, the gap between the validation and training loss keeps increasing. After playing with the model a little bit, I see that it did not improve. We still get the same behavior. The model generates text well. It knows how to end the conversation, but I cannot converse with it. So don't assume that you could take this, you can send a message and you will receive something that replies to what you specifically said to the model. But let's not get discouraged. After arriving at this point, we have trained a base model and we have fine-tuned it. And we saw that in my case, even though I have a small data set, I was able to get something that knows how to model the Darija language. I know it's not superb, but it's not bad either. So that's great. So in your case, if you have a big data set, if you have a lot of conversations, so you could leverage that data and you will end up with a good base model that understands, let's say, English or French or any other language. I did this specifically because the Darija language is, I will say, rare. So you will not find big large language models that are trained on this language. So this is why I try to do this. And I see that this is very promising. I would assume that if I increase the size of the dataset, then the model will be even better. But as I said, let's not get discouraged. We have created the notebooks, so I might return to the first step, train the base model, maybe train a bigger model on more epochs, and then do the fine-tuning again. So yeah, we have every single piece. So the only thing that we need to do is to play with the hyperparameters, to play with the data that we feed the models. After training the model 3 times on this notebook, I think it's time to stop, because we have not seen any difference. In the upcoming videos, we will see how to use adapters. So what we have done in the 6.1 and 6.2 notebooks was full fine-tuning. We fine-tuned the full model. In the adapters video, we are going to attach new neurons and we are going to train those specific neurons in order to create an adapter that we can attach or detach from the base model. See you next time. Hi everyone. In this video, I will show you how to fine-tune the base model using the second method called parameter efficient fine-tuning. We will focus on a technique called LoRA. Let's get started. LoRA is a way to fine-tune models efficiently. It works by adding only a few extra parameters to the base model during training. This diagram explains it. First, we start with the base model and then we add new parameters. These new parameters are going to be trained, and in the end, we get an adapter that we can attach or remove from the base model. In the previous video, we used instruction fine-tuning, which trains the entire model. Here is a simple diagram. We start with the input. During feed-forward, we go through the weights and then we obtain the output. But during backpropagation, we apply this formula. You can see that here we have W. These are the original weights that we started with. And during backpropagation, we try to learn the delta W matrix. We add these two items in order to get the new weights. If the weight matrix W has this shape, we need to update 4 million parameters, which is a lot. Now let's see how LoRA makes this easier. You can see that the diagram changed a little bit. That's because with LoRA, we approximate the delta W matrix using two smaller matrices, A and B. When we multiply them, we get a matrix with the same shape as delta W. Matrix A has dimensions n by r, and matrix B has dimensions r by m. The parameter r is called the rank, and it helps us control how many new parameters we add to the base model. For example, if we keep the same size as before and set r to 2, we only need to update 8,000 parameters instead of 4 million parameters if we decide to use instruction fine-tuning. Now let's start coding. Before I show you the notebook, please make sure to pull the latest changes because I am updating the GitHub repository regularly. Now, open VS Code or your preferred IDE and make sure to open the 7th notebook. And you will see that adding LoRA is very simple. Here we have the same things. I have just copied the previous notebook, which is 6.2 or 6.1. They are similar. And here we are just preparing the data. So here, make sure to load the fine-tuning dataset. Here we are going to use the regex tokenizer, and we are going to load the tokenizer that we saved before. Make sure to tokenize the data, split it, and I'll go through this quickly because, as I said, we have seen this in the previous video, so I don't want to waste time in this section. We arrived at this section where we are going to fine-tune the model with LoRA. First, we are going to create the base model. We are going to add nothing. Make sure to run this. Here in my example, I have 13 million parameters, and here is the checkpoint that I will load. And here is the new section. This is the new thing that I added in this notebook. We are going to add the LoRA layers. Here I have created another script that I called LoRA. It is located here inside the transformer folder. And what it does, it has two methods that we can use. The first one is getLoRa model, and the second one will print how many parameters are trainable. The getLoRa model method will take the previous base model, it will take a configuration and the device, of course, and it will try to add new parameters to it. How does this work? It is very simple. If I go back to the GPT language model class, remember it is located in this script, you can see that we have a lot of linear layers. And LoRA, what it does is it will replace these linear layers with new layers that we call LoRA. And basically it will keep them. It will keep the previous linear layer, and it will add another layer with the new parameters. So whenever you see a linear layer in the GPT language model class, we will replace it with a new layer called, let's say, LoRA layer. And this is exactly what we are going to do in this script. When we give the model to this method, we are going to create a copy of the model, and then we are going to replace the linear layers with LoRA layers. And here are the LoRA layers. It is very simple. So let's start with the LoRA layer. If you remember, I showed you in the slides that we replaced the delta W matrix with two small matrices, A and B. Here they are. And by default, because we did not start fine-tuning, we initialize the B matrix with zeros so that we don't affect the base model. But later, during fine-tuning, the weights in these two matrices will change. So we have A, B, and we have alpha. I didn't talk about this in the video, but this is a value that we can use in order to scale the effect of the LoRA layers. You will see when we are going to use this. And then here is where we apply that multiplication. So if we multiply A and B, we get delta W, and we multiply that with the inputs that we receive, and we have this scaling factor that we can add on top of that multiplication. Okay, so this is our new layer that we called LoRA layer. But as I said, we want to replace the linear layer with a new layer. So here is the new layer that we are going to use. It is called linear with LoRA. Why? Because it is going to receive the previous linear layer. Here it is. And we are going to add to it the LoRA layer. So this is the trick in order to implement LoRA. You keep the previous layer that the model was trained on, but you add to it another layer. In the initialization, this will be equal to 0 because we initialized B with zeros, so it will have no effect on the linear layer. So the model will not be affected. But later, during training, we are going to change the weights in these two matrices, and self.LoRa X will have an effect on the model. And at the end, if we want to save the adapter, we are going to save only the new parameters that we added, which are in the matrices A and B for each layer. So this is how you implement LoRA. And if I go down, Specifically in this method, replace linear layers with LoRA layers, we get the hyperparameters, which are the rank and alpha. We get them from this dictionary, and here is the trick. So here, module.named children. Let me show you what this outputs so that you understand how this works. So I have this notebook that I was using in order to create this implementation. And as you can see, if you take the model and call the named parameters method, this is what you get. Basically, you will get the layers, you will get the name for each layer. So here you have the token embedding layer and you have the weights. Here is the self-attention layer, and here is the first head because we have index 0. Here are the keys, here are the queries and the values. So after converting the model, you see that we added those new LoRA layers. But because we haven't done that yet, here is how we do it. So we loop over all layers, and if that layer is an instance of the linear layer, we are going to replace it with this new class. It's simple, but if that is not the case, we are going to call this function recursively because sometimes we have objects inside of objects. If I go back to the model script, inside, let's say the multi-head attention layer, you have the head layer. So you need to go deeper and deeper into the model so that you replace every layer possible. This is why we use recursion in this example. But if you don't use recursion, then you will have a lot of nested for loops and it will look ugly. So after replacing the linear layers with LoRA layers, we are going to freeze the base model. So here I call this method freeze non-LoRA layers. Let me add an underscore because this should be a private method. And here, remember, if I go back to apply LoRA to transformer, you can see that those layers that were replaced, they have LoRA in them, in the name. So we can detect that. So if LoRA is in name, we are going to train that layer. But if LoRA does not exist in that name, then we are going to freeze that model. So after running this method, the base model will be freezed, but the new parameters that we added, because we replaced the linear layers with the LoRA layers, are going to be trainable. And finally, so this is what the getLoRA model does. It will make a copy of the previous model. It will replace the layers with LoRA layers, and finally it will freeze the base model. And here we have this print trainable parameters. It will print the total parameters, the trainable parameters, and the percentage of trainable parameters to the full model. Now let's close this. Let's go back to the notebook, and here is the method. It's simple, but I wanted to show you what it has inside so that you understand what's going on behind the scenes. Now, if I run this, you see that I get the LoRA model parameter. I get the LoRA model, and if I feed that model to this method, I get 40 million parameters. The trainable parameters are 0.42, and we will train just 3% of the total parameters. And as I said in the slides, if you change the rank value, you will change the number of parameters that you will add to the model. So if I decrease this, then the trainable parameters will decrease. So as you can see, now we have 0.21 million parameters, because remember, matrix A and matrix B are affected by this value. If I increase it, then we will increase the number of trainable parameters significantly. But we want to keep this small so that the training becomes efficient. So I'll use 4, but feel free to change that value. Okay, so now we can, if you want, you can generate from the base model and the LoRA model, and you will see that those new layers that we added will not affect the transformed model because the matrix B is set to 0. After that, we are going to estimate the loss. This did not change. Let's save the checkpoints. I did not change this either. But in the training loop, instead of using the base model, I am using the LoRA model. And make sure to update that here also, because the optimizer should only update the trainable parameters. It should not touch the base model. This is the only change that I made to this notebook. And here, make sure to change the file path so that you save the checkpoints for the LoRA model. So I will run this for, let's say, 10 epochs. I'll change the learning rate to 1e-4, and let's change eval interval to 10. I will run this and I will come back. I am back and the model finished fine-tuning. Let me plot the loss curves. Okay, they look like the previous video, and I will assume that the generations are not going to be good. Okay, so again, the assistant or the fine-tuned model was able to pick the new chat format. That's good, but the text is not good. Okay, so this time it gave me an emoji, but as you can see, I cannot converse with this model. I was expecting this because if we fine-tuned the full model and we did not get good results, using adapters which only add few parameters won't help either. But at least I have showed you how to apply LoRA in order to fine-tune a base model. And in the next video, which I think will be the last one in this course, I will try to revisit the previous steps in order to train a good base model and do a solid fine-tuning step, and hopefully I get better results. I mean, currently we have I would say medium base model, which is not bad. I mean, I'm pretty happy with the results that we got currently with this limited data, but I'll make sure to try to do something solid at the end so that we end this course with something positive. So I hope you enjoyed this video. See you next time. Hi everyone, this is the last video of this course. In this video, I will repeat the steps we learned before, but this time we will use a large dataset. We will increase the vocabulary size and train our model on the cloud. Let's begin. At the start of this course, we used a small dataset with 1.5 million characters. Now I will use the AtlaSet corpus created by the AtlaSet team, which has 900 million characters. This is 600 times bigger than our first dataset. AtlaSet has 1.17 million rows in the training set and 2,680 rows in the test set. Let's look at the challenges of working with big data. With a small dataset, we did not need a lot of resources, but loading the AtlaSet dataset requires a lot of RAM. In this image, you can see that my laptop is using all 16 gigabytes of RAM and also the swap memory just to load the dataset. Now my computer is stuck and I can't do anything else because I have no more memory. Training a tokenizer on 900 million characters will also crash your program because there won't be enough memory left for the algorithm to run. What's the solution? Instead of using the full dataset, train on a small sample, about 1 to 5% of the text that you have on your dataset. This saves memory and helps you estimate the data distribution. Training a tokenizer on big data takes a long time. In my case, I trained it on 10 million characters and it took 6 hours to finish. Now let's talk about file formats. After training the tokenizer and encoding the text into tokens, you must save them to disk because repeating this process every time takes a lot of time and you don't want to waste it. What file format should we use? Should we use Pickle? The answer is no. Let me explain. If you save your tokens as a Pickle file and load it in your Jupyter notebook, you will get an out-of-memory error. This happens because the file loads everything from disk into RAM at once. Never do this if you are working with big data. Use memory mapped file objects instead. Here I used NumPy to save my encoded text in a memory mapped file. This format lets you load only the parts of the data you need. It works like a Python dictionary. You give an index and you get the data that you want. Now, our RAM is happy because the RAM usage is lower and everything runs smoothly. Training the model on this huge dataset will take forever. This image shows that I still have 68 million batches to process. And here it says that I need 77,000 hours to finish training. So I did the calculations and I need to wait until 2033 in order to finish one iteration. That's a lot of time. So my RTX 4070 is not powerful enough. So I will rent a cloud GPU instead. And this is what you need to do. If your GPU is not capable enough, then go and rent a GPU because it is very powerful. You will do the training in 1 hour or even less. So that's worth it. If you want to train in the cloud, try Lambda or Google Colab or Kaggle. If you want free GPUs, then go for Kaggle or Google Colab before paying for GPUs. This will help you get familiar with the environment. If you want to use Lambda, then you need to pay for GPUs. But if you want to go for this, then make sure that you have everything ready so that when they give you the GPU, you will start training immediately so that you don't waste time, because you will pay, I think you will pay, it depends on the GPU that you want to choose, but you will pay per hour. So if you used the GPU for 2 hours, you will pay, let's say $5. If you use it for 20 hours, then multiply that by the factor and you at the end you will get the amount of money that you will pay. So don't waste time if you decide to rent a GPU. Are you ready? Now let's code. After showing you what we are going to do in this last video, here is the notebook that I have created. Basically, I have just modified the previous notebook so that I can load the AtlaSet dataset. And as you can see, these are the numbers that I showed in the slides. And here it says that the training will take forever to finish. Basically, I took the same notebook and here I created a Google Colab. And as you can see, here I have almost 16 gigabytes of VRAM. Locally, I have a GPU with 8 gigabytes of VRAM. So that's not a lot. Here I have 16, so I must be able to train for less time. And here if I go down, here is the training loop. So here it says that I need 25,000 hours to finish this training run. And here I am not using the full GPU power. So what you do is here, I will go back to the top and here I guess I have the batch size set to 2. So this is a very low value. So let me increase that to 16 and you restart the session and run everything. And with Google Colab, it's great because what you could do, so here basically I have cloned my repository. I have renamed the folder to source code because this name is very big. Here I have installed the requirements. So this is what I did in the first 3 cells. And then in Colab, we can connect to Google Drive. If I go to my drive, you can see that here I have uploaded the tokenizer, the encoded dataset. And in Google Colab, I can mount the drive and access the data from it. So here is the path to the tokenizer. And this is how I load the tokenizer that I have trained. And if I look at the vocab, I see that I have everything. So this shows me that it is working. And after that, I create the model, same as before. And here, instead of using from transformer.model, we need to use from source code.transform.model because we have cloned the repository and this is the name that I have gave it. And here, basically, you instantiate the GPT language model. Here we load the data. Again, it is uploaded to my Google Drive. And finally, we do the training. So everything is the same. We have seen this in the previous episodes. And here it says that CUDA out of memory. So we can't load 16 examples per batch. So let's decrease that to 8 and let's restart and see if this will work instead. But still, the training will be very slow because we have a lot of data. And here I want to go through the whole data set. If you want to take, let's say, per epoch, 1,000 examples randomly, then this will work and the training will finish. But because I want to go through the whole data set, that will not work for me. And I cannot fit 8 examples. So let me decrease that to 4. I think 4 will work. So restart and run everything. So this is how it works. You never get things working from the first try, but you should always keep retrying until you get something that works at the end. Okay, let's wait for this and see if the training will work this time. And if you can't use a big batch size value, here I have added this gradient accumulation steps. So basically you take this value and you multiply it with the batch size, and it will simulate large batch sizes. So currently I have the batch size set to 4 and it did not work. So let's go back and set it to 2 and it should work. Lower values are not good because they will slow down the training significantly, but we have nothing to do about it because we are limited with the VRAM that we are given. And this is, remember, this is just the free tier. So this GPU that you get here is free, and look at this value, because this runtime is given, because free GPUs are not available always. So you get a certain amount of time so that other people can use them. So here in my case, I have 3 hours left. And after that, I need to wait for some amount of time in order to get the GPU back. So here I was saying that you take this and multiply it with the batch size. Currently, the batch size is set to 2. Gradient accumulation steps is set to 8. So this gives us 16. And this simulates basically a batch size of 16. You can increase this value to simulate large batch sizes. And here the training is going. And I think after 100 iterations, we will evaluate the model. So let me wait for this to go up to 100 and evaluate the model. And inside the evaluation method, we're not going to evaluate the model on the whole data set because that will take a lot of time again, and we want to spend most of the time training the model, not evaluating it. But at least we are taking 1,000 examples and evaluating the model on them. And these examples are generated randomly with this getBatch method. Because if you go inside, as you can see, we are using tosh.randomInt to get a random index. And then because we are using the memory mapped file object, we are going to get the portion of the data that we need. And we are not going to, you can see that here, the system RAM, we are just using 4 gigabytes. But if we were to load the whole data set, then we are going to, this memory will be filled very quickly. So let me go down. Okay, so now we are evaluating the model because we have reached the 100th iteration. So now let's wait for some time and I will come back. Or actually, let me just show you the other providers. So here we have Kaggle. Here you can see that here you can create a notebook, or if you want, you can upload your own notebook. But here you can see that here you have the CPU, the RAM, and disk storage. If you want to enable accelerators, so in Kaggle they call them accelerators, you can come here. Here it is set to none, and choose the GPU that you want to use. Or you can go up to settings, accelerator, and choose the accelerator you want. And here in Kaggle they give you 30 hours. How do you know that? Basically, let me go back here. If you click on your profile, you see that here you have, here in my case, I have 30 hours available so that I can use the accelerator. If you don't see this, this means that you need to verify your account. So go to settings and here, verify your account. After verifying the account, here it says verified, you will be able to use the GPU. And finally, I mean, there are more providers, but these are the 3 that I wanted to show you. So Kaggle, Google Colab are free. They have free tiers. This is what I want to say. In Google Colab, here they say that if these GPUs that they have in the free tier are not capable enough to solve your problems, then you could go and buy subscriptions. Basically use Google Colab Pro, and this will give you access to other GPUs. So if you click on runtime, change runtime type, you see here are the other GPUs that they have if you decide to go to Pro mode. And finally, I have Lambda. This is what I showed in the slides. Here are the GPUs that they have, and here are the pricings. You can see that here is the VRAM. This is what we want. We were limited by this value. And here, the lowest tier or the cheapest, I will say, GPU it has 24 gigabytes of VRAM. That's good. And you will pay $0.5 per GPU per hour. But if you want to go up to the GH200, it will give you 96 gigabytes of VRAM. That's a lot. You will have a lot of RAM and a lot of storage, but you will pay 3 times the price. This is the tricky thing about these things. If you want to train the model freely, that will take you a lot of time. So if you want to buy time, go and rent a GPU, and you could do the training in 1 or 2 hours, and you will pay at the end $3 or $5. It's not that much. And at the end, you will get something that works really well, and it will save you a lot of time. So I wanted to show you the free alternatives. If you want to start with them, this is what you should do. And this is what I did currently, because I have never rented a GPU before. So this is, for me, it's the first time doing this, like you. So I started with Google Colab. I see that it's not going to help me because I am bottlenecked by the GPU available, so the VRAM is not enough, and I cannot increase the batch size. And the batch size is very important in this case because it will allow us to move through a lot of examples in each iteration. So, and here also I am limited by the RAM. So if I want to load the whole data set by using, let's say, any GPU here, I will get 100 gigabytes plus. That's a lot of memory. So I could load the whole AtlaSet dataset without any issue, without using the memory mapped file object. So these are things to take into consideration when choosing what GPU to rent. And also here, this is just one GPU. If you want to use multi-GPU training, then click on the other options. But remember, these are going to be costly. So you will, if you decide to use 8 GPUs, then you will pay 8 times the price. But here, I think 1 GPU is enough. So when I will go through Google Colab. I will wait for this to train for, let's say, an hour, and then stop the training, look at the loss functions, and then start to evaluate the model. And here, even though you see that here, how many values are here? So I think this is 136 million batches. That's a lot. We could, for example, stop the training at any time and evaluate the model, because at least we will get something that was trained for 1,000 epochs, 1,000 batches or 2,000 batches. We don't need to go through the whole data set because it's relatively big. Also, I want to show you, here is the AtlaSet dataset. It is available on HuggingFace. This is how I loaded it. It contains 2 splits, the training splits and test split. Here in the training split, we have 1.17 million rows, and on the test set, we have 2,000 rows. So basically, I looped over all examples, and here is how I extract the text, and I concatenated that into this, or I appended everything into this list. And at the end, I converted that into a sequence of text. And finally, I saved it as a text file. Here, I am just showing you how to load a dataset from HuggingFace. But if you are not, this dataset is in Arabic. So maybe you are not interested with this dataset. But if you want to load a dataset in English or French or Chinese, then look for the dataset that solves your problem and change the name here in the load dataset method. So after saving this, then I went to the Byte Pair Encoding notebook. I have loaded the dataset, and here, as I told you in the slides, the dataset contains 900 million characters. That's a lot. If I try to load everything and train the tokenizer here with the train method, I'm not able to do that because loading the whole dataset consumes all of my memory, and trying to train the model will crash VS Code every single time. So what I did instead, I will just read the first 10 million characters from the AtlaSet dataset and train the BPE algorithm on these 10 million characters. This helps prevent the out of memory error, but still with 10 million characters, this process took 6 hours. As you can see, it took 6 hours to train the BPE algorithm on 10 million characters. Just imagine if I tried to train the tokenizer on 100 million characters, or let alone 900 million. So that would have taken days and days to finish. And here I also increased the vocab size because we have increased the size of the data set. After training, basically you go through the rest of the notebook and you save the new tokenizer. And after that, I have basically came to here and I have rechanged the notebook so that I can. And one thing before that, so after encoding, after getting the tokenizer, I encoded the AtlaSet dataset. And here, this took, I think, 45 minutes to finish. I was, again, tokenizing 100 million characters at a time. So don't try to encode the whole dataset at once, because that will use a lot of memory again. So here, I decided to tokenize 100 million characters in each iteration. And at the end, I ended up with a dataset that contains 300 million tokens. That's a lot. When we started this course, the dataset that I had contained just 300,000 tokens. That's a lot of difference. That dataset was very small, but this one is big. And at the end, as you can see, I am saving this as a NumPy array. And here I am deleting it just to free up memory. But after running this cell, just restart the notebook to free up the memory. And then if you want to use this as a memory mapped file, when using the load method, just provide memory mapped mode to read only. And here is, after loading the dataset, it will not consume the whole memory. So here it's just showing you the shape, but it is not loading the values. Okay, so these are the things that I have done in order to prepare the dataset and in order to prevent the out of memory exception. And do you want to do this process locally? Because, I mean, you could do this here in Google Colab if you want, but don't do that here, because here because this process takes hours and you will be charged for those hours and you did not train. You want to use this just to train the model. So the pre-processing should be done either locally or try to rent a VM that doesn't have a GPU because it will be cheaper, and do the pre-processing there. So this is, I want to warn you, never do the pre-processing when renting a GPU, because you want to use those just for training. So that's it. Here we were able to evaluate the model after the first 100 batches. And here we are evaluating the model again. So I will wait. Let's train the model for 1,000 batches and I will come back. Okay, so I have stopped the training because it was taking a lot of time. So here I trained it just on 500 batches. Here you see that the loss is fluctuating. And this is because when we enter evaluation mode, we take 1,000 batches randomly. And in the dataset, we have millions of batches. So this is why each time when we evaluate the model, we see different values for the loss. But if we kept training further and further, then the model will have seen a lot of examples and then the loss will adjust accordingly. But let me just copy this. So this is exactly what I got here when I was training the model locally. You can see that the loss was fluctuating and it stayed relatively the same. Here are the values. So let me remove this. I don't need it. And let's just take this. I want to see the generation. Okay, so here we have evaluation mode. We are generating 50 tokens. Okay, so let's see. Okay, not bad. Yeah, this is not bad actually. So the model was able to pick some text from the training set, and this is not bad for 500 epochs. So, but as you can see, the problem is that with this approach, we need to wait a lot. Instead of looping over the whole dataset, because this is what I was doing. So here splitting DAX, let's see. So total data to process is equal to this value. So here we have 273 million batches. That's a lot. So what you can do instead is that in each iteration, take, let's say, 1,000 or 10,000 batches and do this for 100 epochs. And then you will get at least a model that was trained on, let's say, 100,000 batches instead of waiting to train on the whole data set. Or if you don't want to change this, then what you could do is the same thing that I did here. So train as much as possible let's say train for an hour or two, and then just stop the training. And then you will get the latest model that was trained on the latest batch, and use that model and see if it works well or not. So as I said, Google Colab and Kaggle are similar. Both of them give you free GPUs, but don't forget that here the training will take a lot of time. And another factor that affects the training speed is the size of the model. Here I have increased the size to 55 million parameters. Before it was, I think, 11 million. Also, don't forget, when you finish, disconnect the runtime so that you give other people access to the GPU. And yeah, that's how you train on Google Colab. And finally, if you decide to stop the model, because here I am saving the checkpoint after 10,000 batches, at least try to run this manually after you stop the cell from running so that you save the model, the checkpoint at the last checkpoint. Okay, so now I have disconnected the runtime. I'll close this and I'll close Kaggle and go to Lambda. So the first thing you need to do here is to log in. So let me click on this button. I think, yes, I have already created my account, so that's why I logged in automatically. And then you need to go to settings and enter the credit card. Because if you try to launch an instance, you will not be able to do that because you need to attach the payment method. So just click on add payment method and you will go immediately to settings to specify or to enter that information. Okay, so I have tried adding my credit card and it did not work because I was not expecting this. So here they say that the purchase is being made from a country we don't support. This is the error that I got, and here are the supported countries. And I live in Morocco, and I cannot use a VPN to pretend that I am from one of these countries because they will flag that as suspicious. So that's bad. So now I need to look for another provider. Okay, so I am back and I have changed some things in the same notebook. So I will clean it and add it to the list of notebooks later. But what I did, so here it says that the estimate loss function is not defined. So let me run everything. Let's run this. So now it should work. And here is, as you can see, it is saying that the training will take 5 hours. So that's not bad. Before it was saying 80,000 hours or something. So let me show you. And here I am using 6 gigabytes of VRAM. And I still have 1 gigabyte left that I can use if I want to. And the model size is, I think, 30 million parameters. Yes, 39 million parameters. So that's relatively big. Here I have 1,000 batches that I will use to estimate the loss. But here is the change. Here I have two methods, the overlapping batches and the non-overlapping batches. You know, each example contains 1024 tokens because this is the block size that I chose. So to go to the next example, we will shift the index by 1. So this is the first method, overlapping batches. And this is why the size of the training was big, because we were overlapping the data that we have in the training set. But in the non-overlapping batches, we first try to calculate how many non-overlapping blocks. So let's say that I took the first 1024 tokens. The second example will skip the first 1024 and take the next block size. And this way we will have non-overlapping examples. And this is why the number of blocks is reduced significantly from, I don't know how, I think it was 69 million or something to 66,000. That's a big difference. So I think instead of running this on the cloud, I think I can run this locally. So 4 hours is not that much. So I will just increase the performance and wait for this to complete, and I will come back. I am back, and as you can see, I have pre-trained the base model on this AtlaSet dataset, and I have done this for 42 hours. Let me show you. So here, 42 hours is a lot of time. So I didn't leave my laptop on for 42 hours. That's a lot. So what I was doing here, I was training one epoch at a time. So one epoch was taking 6 hours on average. So I trained for 6 hours. I save the model, and then another day I come back, I load the checkpoint, and I train again. And just to show you, in the output folder, if I open pre-training base, because here I was experimenting with different model sizes. Here, as you can see, I have the checkpoints. So this is the first epoch and this is the 6th epoch. So this gives me, I have another epoch, but I forgot to save it. But in total, I trained this model for 42 hours. And sadly, I did not show the loss functions because I forgot to concatenate the lists so that I showed the loss from the first epoch to the last epoch. So I forgot to do that. This is why I did not plot the loss. And here, when I was inferencing the model, here you can, if you know how to read Arabic, this is good text. It's not that bad. I will take it. I will open Google Translate. Let me paste this and let's start reading. What are the main reasons that made the French remain impressed, but the Europeans were based on the idea of where was Heard and this. So you can see that, the text is not coherent, but the model knows how to put words together. This is just a base model, so don't expect it to give you accurate responses for hundreds of tokens. At a certain point, that will degrade and the model will start doing something else because it was not instructed to do something like answering questions or discussing with a user in a conversation manner. So let's go back to the notebook. So this is what I did, and I have created the notebook so everything is clean. And then I started doing the fine-tuning. In the fine-tuning, as I said, you can fine-tune the model to do basically question answering. This is QA. This is the first version or the first fine-tuning that we can make. And I also created a supervised fine-tuning dataset. I have created it manually and it is available on GitHub. The dataset is very straightforward. We have two roles. We have the user role and the assistant role. And as you can see here, we have a list because this is a conversation. So in dataset, we have a list of conversations. And in each conversation, we have two roles, the user role and the assistant role. In QA, what you do, you take the user role and you expect or you train the model to generate the assistant role without any context. You could add another field, which is called context, to help the model understand how to generate the answer, but this is the basic form of QA. Here, after loading the dataset, I have one-on-one conversations. Let's load the tokenizer. And here I have a system message. So if you want the model to behave in a certain way, make sure to add this system message before the user question. Here is the system entry. In this cell, I am trying to make sure that all conversations do not exceed the block size. When I run this, I see that the longest entry in the dataset contains just under 500 tokens. So we are good to go. And now we need to add special tokens to our QA pairs. Here are the tokens. We have start turn. This marks the start of a turn. End turn, we have the separator and end of text. The format message is simple. For example, if we take the user turn, we will start with the start turn token. Here we are going to have either user, system, or assistant. This is the roles that we have. Then we are going to add a separator to separate the role from the message. And finally, we will end this turn with the end turn token. Now we are going to create our fine-tuning data. Remember that inside the JSON dataset that I showed you on my GitHub repository contains a list of dictionaries. So we need to turn this into a list of QA pairs. How do we do this? It's simple. So we get for each conversation in data, we are going to loop over the messages. If this is the user role, we are going to add the system message. This is optional. If you don't want to add system message to the QA pairs, then remove this line. You don't need it. But if you want to have it, then before taking the user role, make sure to add the system message. So we are adding it to this concatenated messages string. And after that, we add the user role because message contains the user role. So this is the first turn in conversation. It is going to be the user turn. After that, in the second iteration, we are going to get the assistant turn. We are going to do the same thing. We are going to add the message, but this time we need to end this string with the end of text token, because this is an example that the LLM will be trained on. And after that, we tokenize this message, we add it to the fine-tuning data, and then we start over. So we are resetting for the next QA pair. So this is what this cell does. And if I print the length, I get 256 QA pair. If I print the first one, you can see that here, this is start turn. So this is the system prompt. Here is the system message. We end that turn, we start the user turn, and finally we start the assistant turn. And at the end, we add the end of text token. So this is how the QA pairs are going to be formed. If you remember, because we have different sizes, we need to make sure that our training examples have the same size so that we can batch the data so that we train efficiently. Before, what I used to do, basically I just keep padding until I reach the block size. But because sometimes we have just few tokens, we are going to add a ton of padding tokens, and this is wasteful. So what I will do instead, I will try to compute the maximum sequence length from the fine-tuning data. And here it gives me 331 tokens. And then I'll just keep padding until I reach this value. This is more efficient instead of padding until I reached 1024. So this cell, I haven't changed it. This is exactly what we have done before. And you can see that here I only have the training set. I will modify this to add the validation set, but because I was just experimenting with this, I only have the training set. So if I run this, you can see that I have 256 examples, and each example has this shape. So the max sequence length is 331. Now we create the data loaders. Again, I'll come back and I will add the validation set shortly. And here the batch size is 16 because we are working with smaller sequences. So we could increase the batch size a little bit, and then the rest is the same. So you load the checkpoint. So this is the base model, and here we are loading the latest checkpoint. Good. So all keys matched successfully. If you want to use the base model for inference, just to make sure that the weights were loaded correctly, you can do that here. This is the estimate loss function, save checkpoint. So they did not change. And here we have the training loop. Also, this wasn't changed. The only thing that we changed is the dataset. And now you can train. So I have done that. So I have trained for 100 epochs. And here, because I only have like 100 conversations, it's not that much. So the model will overfit the data quickly. And this can be seen. So here we started, the training loss was 6.8, and we immediately the loss went to 2 and then 0. So because the data distribution in the fine-tuning dataset is not that large, the model is able to learn it very quickly. But even if the model will overfit, I'm just doing this for experiments because I'm saving the model after the end of each epoch. So even if it overfits at, let's say at epoch number 10, I can load the previous checkpoints where the model did not overfit. So this is what you do. And then, so let me clear this because we have a lot of things in the output. So you can see that the plot, this is how it looks like during training. So yeah, I have trained this a lot, but I could have trained just for 5 epochs or 10. And then in inference, I will explain the code, but just to show you how the output looks like, here it is. So I have asked the model, what is your name? It said the name because I have mentioned this in the system prompt. And then it said, is there anything I can help you with? So this is good. But because, as I said, because the supervised fine-tuning dataset is so small, if I ask something that the model has never seen, it will hallucinate things. It will say things that are not good. So let's try this. Here is the new prompts that I will ask the model. Who won the 2006 World Cup? I know that this information does not exist in the supervised fine-tuning data because I have created it. So let's see the answer. Okay, so the model says here Argentina. Is this correct? Let's see. And the answer is Italy. So as you can see, this is just to show you that the model does not, I mean, if you have a good base model, because here the base model that I have trained has only 40 million parameters, and I have trained this for 42 hours. I could have trained it for 100 hours or two. I mean, 100 hours it's a lot. But still, the model is not that big, so it does not have a lot of parameters to memorize a lot of information. So this is a limitation, but the solution is very simple. You see that, for example, open source models have very big sizes. One of the latest models that was open source is Gemma 3 from Google, and the model has billions of parameters. And currently, my base model has only 40 million. So you see, there's a huge gap in both the model size and the training dataset size. But as I said, the solution to this is easy. Just keep scaling and you'll have good performance at the end. Okay, so I have showed you what I have done. Now, let me go back and add the validation set or the validation to this so that we can see when the model overfits in the plot. I mean, yes, it is very easy to see whenever you see that the loss reaches 0. That's a good sign that the model was overfitting. But let's also add the training loss, the validation curve, so that we can immediately recognize when the model was overfitting. I have updated the notebook and I have added the validation set also. So let me run these cells. Okay, we have seen these things. Okay. So here, when we get the training data tensor, we are going to split it into two sets. We are going to take 95% of the data as training, and the rest will be in the validation set. So here are the numbers. We'll have 243 QA pairs during training and 13 during validation. Let's make sure to run this cell. And here I have added these two variables so that I can use the validation loader during the loss estimation. And here I can get a batch from the training loader and the same for the validation loader. Now let's load the checkpoint. I will not use the model for inference. Inside the estimate loss, I just copied this from the previous notebooks, so nothing new. Here I have added the validation losses list, and when I call the estimate loss function, I make sure to pass the validation loader, and we get the losses dictionary. From it we can extract the training loss and validation loss. So now let me run this, and here, before running this, make sure that whenever you fine-tune a model, to use a small learning rate so that you don't change the neurons or the weights abruptly, so that you change them smoothly. And here I will just train for 10 epochs. So iterations here means epochs, because we saw that here, for instance, that we quickly reach, a low value for the loss. So I don't want to go for more than 10 epochs, and we will see. Maybe we need to train for less than this if the validation loss starts to go up. But for now, let's just train for 10 epochs, and I will do the evaluation after 2 batches. So let's run this. And here, let me bring Ghosty. So as you can see here, I am using 6 gigabytes for the fine tuning. And let's see. So we started at around 7. So far so good. Both train and validation are going down, and we are still on the first epoch. So as you can see, the loss starts going very, very quickly. In here I used 1e-4 as the learning rate. So we could, for example, use 1e-5 to slow down the speed at which the loss is decreasing. But so far so good. There is no sign of overfitting. So I'll wait for this to complete and I will come back. I am back and the training finished. So it took just 3 minutes because the dataset that I have is not that big. So let me clear everything. And here I will plot both training and validation loss. And as you can see, the curves looks great. At the end, we start to see that the model was not improving further, but there is no overfitting. This is good. So let's use this model for inference. Here I have changed the folder to run number 2. Let me see how many checkpoints I have. So let's take the first one to see if the model was able to pick up the answer format, because here, you remember, we are using special tokens to form basically the input and the output. So let's ask the same question: who won the 2006 World Cup? Okay, as you can see here, the model is generating. So here is basically it's generating random stuff because this is the first iteration. So this is completely nonsense. And also I want to mention that inside the GPT, if I go here to the model script, we already had the generate method. Now I added another one, which is called advanced generation. I mean, if you have played a little bit with LLMs, these concepts are familiar to you. Temperature, top K, top P are used to basically, when we generate from the model, we can alter how the model generates responses. Here, basically in the generate method, we were getting the probabilities and we were getting the token that has the highest probability. This is called greedy because we will always have these same answers. But here with these three variables, whenever we run the notebook, we will get different responses from the model. And yeah, basically this is an advanced generation method that I have added. And this is exactly what I used here. Okay, so this is the first checkpoint. The model was starting to get familiarized with this new format. Let's go to the third epoch and let's see the output from the model. The good thing is that the model was able to basically generate the end of text token, because here I was generating one token at a time, and I will stop if I get the end of text token or the end turn, because at the end we will have end turn and end of text tokens next to each other. So yeah, this means that the QA format that we created, the model was able to use it or to get familiarized with it. So basically we start with the system prompt. Here it is. So this is the input. We start with the system prompt. We add the user message and we add the assistant, but we stop here. And the model, because he was trained on many examples in this format, knows that it should continue this format and it should only generate the answer part. But here the answer has nothing to do with this. So let's go and check the 6th checkpoint. Okay, so nothing. Let's go to the 9th checkpoint. And as I told you, here we can play with these values to basically get different responses. As I said, this question does not exist in the data, but this is why I'm not getting a correct answer for this. I will change this to ask, because in the system prompts, I gave the model a name. So let me ask about that. Okay, so I have asked the model, what is your name? And it was able to give me the name that I mentioned in the system prompt. But I don't get this answer all the time. So sometimes I will get this answer. Sometimes I get other answers that are not related to the question. I'm assuming that because I have a small base model, I was not able to get a model that understands the language very well. Because here, if I ask the question differently, the model might respond differently. But at least we have been able to get something that works very well from where we started off, because we have scaled the pre-training data. I have created a supervised fine-tuning dataset that works very well, that contains a lot of topics. So yeah, I mean, if you want to get something that works even better than this, as I said, all you need to do is to increase the model size, to increase the data, and eventually you will get something that understands a lot of things in your language. And at the end, if you want to get something that works well, you can use QA like what I did here. Or if you want, you can formulate the problem so that you use the whole conversation, so that you can so that you can talk to the model in a conversational way. Because here, if I ask something that is related to something that I said previously, the model will not have the context. So we need to train on that format. And this is why I have created this supervised fine-tuning dataset, because it is formed from a lot of messages, and those messages are combined into conversations. So currently we have done QA. Later I will try to basically modify this notebook so that I can train with the context. But again, because here we did not get something that understands the language very well, I'll assume that even if I train on the whole conversation, sometimes I might get some good results, but not all the time. But this is expected. I have limited resources. I can't train very big models on my laptop, but maybe in the future I might do a bigger training run if I keep gathering more data, and hopefully I get something that works very well on the Moroccan Darija language. We have reached the end of this video. As you can see, I have added many notebooks, so I will make sure to clean them, and then I will push them to the GitHub repository. I hope that you found this video very interesting. Maybe this video will be the end of this course. This is what I said in the previous video, but maybe I might add other notebooks so that I show you how to use, because here we train the model, we train the models, we train the tokenizers from scratch. We have used only PyTorch, but to run these notebooks, you have to do a lot of work. So if you want to go very quickly, maybe I'll add those notebooks to show you how to use those classes, because I mean, you have just one line. You create a class and then you call the train method and you are done. You train the model, you push it to HuggingFace, and later if you want to retrieve it, you can do that. So yeah, maybe I will add a video on that, and I will see. I'll try to do the fine tuning with context, with conversations. If I get good results, I'll make sure to make a video on that. But if I don't get promising results, I'll just make sure to include the notebook, and I don't think I will make a video on it. Keep an eye on the GitHub repository. There you will find if I have updated it or not. See you next time. Hi everyone, welcome to this bonus video. In the previous one, I have said that I will try the conversational format, and if that worked, I will upload another video. So we are watching this video. This means that the conversational format worked great. So this is the previous method that we used. We used QA. This is how we structured basically the inputs. And now I have added two other notebooks. So let me close this one. So here we have let's scale fine-tuning conversation, but with no masking. Here we have two methods. So it's the same thing. So we are using the conversational data. We can add a mask or not add it. So let's start with the first one, no masking. Look, everything will stay the same. The only thing that will change is this diagram that explains how we form the data that we will use in training. So here is an example of a conversation. We have the system message, user assistant, and you can keep adding more turns to the conversation. If you want to exclude the system message, you can do that. So the first thing you do is you take the first turn. So this is what I have done here. I took the system message, user, and assistant, and we will consider this as an example that the model will be trained on. And then the difference between this and QA. So this is QA. The second iteration will be to include the next turn. So here we still have the first turn, but we added the second turn. So you keep increasing the size of the example until you finish using all the turns in the conversation. And in each example, you add the end of text token. And here, look, so here we have system, user, assistant. And here in the assistant turn, so you can see that here start turn assistant. At the end of that turn, we add the end of text token. But here we remove it. So let me find the first assistant turn. So here is the first assistant turn. You can see that here we have start turn, assistant, here is the message, and here is the end turn. And you can see that we have omitted the end of text because we are going to add it to the last assistant turn. So here you can see that here is the last assistant turn, and we add the end of text token. And this will teach the model that the only thing that varies is the end of text token. It will notice that we add this token whenever we end the assistant turn. And this will steer the model to basically try to complete the sentence and end it when it answers the question, and not continue the generation. Before I did not do this. So basically I converted everything into one giant example, and then the model was trying to mimic this structure. So when I start by giving a question, the model will generate the assistant turn, and then it will not generate the end of text when it finishes that turn. It will start generating the user turn, then the assistant turn, and it will never stop. I mean, it will stop at some point, but we don't want the model to mimic the data. We want it to answer the question and then stop. So by doing this, we teach the model that the only thing that varies is the end of text token, and you should place it when you finish the assistant turn. As I said, this is the only thing that changed, and here is how I implemented that. And again, just to show you that this is exactly the same thing, I have here, this is the previous notebook, and here is the new one. So you can see that here we have the tokens, this is the format message function, and here, when we arrived at the assistant turn, basically we concatenate the message, and then we add it immediately to the fine-tuning data and start over. So here, with this approach, we are going to have only QA pairs in the fine-tuning data list. But here, notice that everything is the same. When we arrive at the assistant turn, we are going to add that to the fine-tuning data, but we are not going to reset the message. We are going to keep adding to the concatenated messages string. And another difference is that here we want to add the system message only if this string is empty, because we don't want to add the system message in every turn. We want to add it only once. And another change that I have made, look at here. In the assistant turn, we add the end of text token before tokenizing. But here I don't do that because, as I said, I want the end of text token to appear only at the last occurrence of the assistant turn. So this is what I did. So I only add the end of sequence or the end of text token if I want to tokenize that sequence. So as I said, this is the only difference between this notebook and the other one. So let me close this one. Let me increase the font and let's look at the rest. So here's an example. So if I look at the first example in the fine-tuning data list, you can see that here is the system message, here is the user's turn, and the assistant turn. And as you can see, we have the end of text token. So because I know that the first conversation has multiple turns, so the second element in this list will continue on this. Look, here we have this string. It's the same one as this. And here we have the end of turn token like here, but we removed the end of text token. So the next turn should be the user's turn, and here it is. So then the assistant starts replying, and at the end we add the end of text token. And we keep doing the same for the rest of the entries that we have in the dataset. So this and the rest stayed the same. And then I want to fine tune the model. Here is how the loss looked like. So we have the training loss and validation loss. And here we start to see a sign of overfitting because the gap between the training and validation loss is starting to grow. So, but as I said, here in the training loop, I have made sure to save the model after the end of each epoch so that if the model overfits, I can easily load the previous checkpoints to get a model that trained well but did not overfit. And then in inference, we load a checkpoint and start asking the model. And here I made sure to change the code so that we can have a conversation. Here is an example. So I said, what is your name? The model responded with the name that I gave it. And then it said, is there anything I can help you with? So I asked how many planets are in the solar system. The model replied by saying, in our solar system. Then I said, yes. The model asked the same question, in our solar system. I said, yes, in our solar system. And then it said, in our solar system, there is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So you can see that the conversational format is working, and the model stops when it answers the question. And then I said, thank you. And then the model said, you are welcome. If you need anything else, just ask me. Again, this notebook doesn't use any mask. Now, what is the difference between no masking and masking? Let me explain. So I will close this one and go to the other notebook. Okay, again, everything is the same, but here is the change that I have made. Here I have just one turn because I don't want to complexify this diagram. Here we turn this into a sequence of tokens here we have a sequence of text, but later we will convert that into tokens. And then here is what we mean by masking. Before, in the no masking version, the model will see this sequence and it will learn to generate everything. So we will start by this token and the model should learn to generate the system token. But we don't want that. We want the model to take the input, which is the system message, the user turn, and then generate this part, the model answer, the end of turn token, and the end of text token. So the previous method worked because basically the system message is fixed, so the model can learn that during training, and the user turn is also fixed because we have these tokens. The only thing that changed is the question. So by using no masking, the model should learn to associate a question to an answer. But that's a lot of work. What we want is to mask this part. So this part will be used as an input, but the model should not learn to generate the system prompts or the user question. The model should only learn to generate this part that it is not masked. So in the masking notebook, we are going to mask this prefix, I will say, and only evaluate the model when it starts to generate the rest of the sequence. Let me show you how we did this. So here, when we formed the data, nothing changed, but we made the change in the data loader section. So here, when we create the X and Y pairs, I have added this method, apply mask to target, because when you want to mask, you don't mask the input, you mask the target, because during the loss computation or the loss calculation, we use the categorical cross entropy. So let me go to the model script. Remember, we have this ignore index that we added as a parameter to this class, and we are using it here when calculating the loss with the help of the cross entropy loss function. When we mask those tokens, basically we are not going to punish the model if it does not generate the system prompt very well. We are going to punish it if it does not generate the assistant's answer very well. So this is the ignore index that we are using, and this is what we want to add, or this is what we want to apply to the target. So let me open that image. The apply mask to target will apply the mask to this section of the target. How am I doing this? So you can see that here in the assistant turn, we have this string, start turn, assistant, separator. This is what I have here. So start turn, assistant, separator. I am encoding this and converting it into a tensor. Why am I doing this? Because I want to search for this sequence of tokens in the target so that I know which indices I should mask. So here we get the assistant turn tokens. Again, this is a tensor. Here we have the list. We are getting the length of that sequence of tokens, and then we try to find the last occurrence of the assistant turn. Why? Because here, remember, here we only used one turn from the conversation, but if we had 2 or 3, this start turn, assistant, and separator sequence will be repeated 3 times, and we want to take the last one. This is why I said that I want to find the last occurrence. So last occurrence by default is set to -1 because we don't know where it is, but then we are going to use a sliding window approach to find this sequence of tokens. So you see that here we use torch.all to compare 2 tensors if they are equal, and here in the target, this is the window that we take. Basically, this is a slice from the target, and we are comparing those tokens to the tokens that we got after encoding this sequence. If we find it, then we are going to change last occurrence to this value. And here we are not using I because I will give us the start turn. We want to get this. So we are going to add the length of this sequence so that we arrive at this point. And after the for loop, after finding the last occurrence, we are going to replace everything from the start up to this point with the padding token, because this is the token that I am using as a masking token. If you want to use -100 or another value, feel free to do that. But make sure to inform the cross entropy loss function, because it needs to know which index to ignore. Because if you don't do that, then nothing will happen. Here I have used the padding token, and when I instantiate the GPT language model, I gave this token as the ignore index. So this is how we apply the mask. And here, this approach works only if you use right padding. What do I mean with right padding? So if you add the padding here at the end of the sequence, this approach works only for that case. If you decide to add the padding to the start of the sequence, then we should revert this, and instead of starting at index 0, we should start from the end of the sequence and find the last occurrence. So here I should add a note that this only works if you use right padding. And the rest is the same. So here we have batch size, and let's look at an example from Y. I don't know if I have restarted this notebook. Great, I didn't restart it. So let's take the first example. And here, as you can see, so the padding token is 16,388, and this is the part that we have masked. This is equivalent to this part that I have colored in black, and the rest is the assistant answer. And if we compare this to the input, you can see that the input is not masked because we want to take everything and give that as an input and start predicting these tokens that come after the system and user terms. And at the end, we have, this is why I said that here I have used the right padding approach. Awesome. So this is actually working. And then the rest stayed the same. So I have created the model. Here is where I specified that the padding token is used as the ignore index. So I loaded the model, I started the fine tuning, and then this is the loss that I got. And here, because I only compute the loss for few tokens, the loss was bigger, and we start to see a lot of overfitting for this model. But again, you have the previous checkpoints, so you can load them. And then, so here we load one of them, and we start chatting with the model. Again, I always start with what is your name, because I have mentioned this in the system prompt and I want to see if the model learned this or not. And sure enough, it did. And then I said, how many minutes are in a day? And then it said to me that in a day, we have 1,440 minutes. And here it said that in our world, there is roughly 1,440 minutes in a day. So I find this interesting because I didn't mention this exactly like this in the fine-tuning dataset. So, but the model is trying to be a little bit creative, because remember, we are using the advanced generation method, and we can play with these values to control the behavior of the model. If you use the generate method, then the model will give you the same answer every single time. So the model will not try to be innovative. And then I said, thank you. And it said, if you have anything, just ask me. I've also added this part. So if you want, let me show you why this one is important. So if I run this again, so it gave me the answer. If you ask a follow-up question and the model doesn't give you something correct, if you don't like the answer and you want to retry, if I try to do this, we will add another entry to the conversation, but we don't want to do that. To do this, just uncomment this, and this will remove. So let me show you how you do this. So here is the answer, here is the question, and here is the answer. If I don't like that answer, or if I want to see if the model generates something else, I will come here, uncomment this, and generate. And you can see that here we did not add another entry to the conversation, but we removed the previous entry and we replaced this with a new one. So you can keep repeating until as you can see, because we are using this method, each time we get something new from the model. Great. So I'll uncomment this, and yeah, that's it. So this is what I wanted to show you in this bonus video. I was surprised because this worked. I'm very happy with the results. The model is small. So this is just a 42 million parameter model. Let me double check that value. Yes, as you can see, the model has only 42 million parameters. The dataset that I have used during pre-training contains 900 million characters, which after tokenizing it contains almost 300 million tokens. It's a big dataset compared to the first one that we have used in the start of this course, but still the model is not that big. So I have seen during inference, when I was testing the model, that it doesn't understand a lot of concepts. And if I try to ask different questions that cover a lot of topics. The model doesn't know how to answer that because it is small and it doesn't know, as I said, different topics. It doesn't know how to answer if the question is out of this distribution. So these are the limitations that I have found, but overall this is great. And I think the next step is just to increase maybe the size of the model, increase the size of the supervised fine-tuning dataset to get an assistant that works well in your particular language. I hope that you have enjoyed this series. This is the last video. I'm sure that I will not upload other ones, and I hope that you enjoyed it. Feel free to reach out to me if you have any questions, and I will be very happy to help you achieve what you want to achieve. See you next time.